And welcome, ladies and gentlemen, to a very exciting episode of PASCO Live. I'm JP, and today the P stands for physics. In fact, an entire day of physics. Not just one experiment, but we actually have 17 total experiments in physics to show you today. And if that's not exciting, we have our entire complement of physics personnel here at PASCO Scientific going to show you the greatest things in physics, the greatest demonstrations you can do, the best things you can bring into your classroom. And the really wonderful thing is we're live. So if you have questions, we're standing by to answer them for you. We've got our domestic sales folks, our international sales folks, and all of our physics specialists are online today to answer your questions. And you're going to recognize so many of our people that join us every single week for PASCO Live, like JJ Plank. JJ, what do we got lined up today?
We have a lot of amazing physics demos, showcasing PASCO products. Whoops. As well as, did I mention we're live?
Yes, and a lot of great things that will happen live. Keep your eyes for the mistakes. We hope not to make any, but we do. We have a lot of great things. In fact, we've got rolling carts sitting in the back, right?
Yeah,
and you've got right. Looks like you've got a whole lineup on the list today.
Oh yeah.
Plus, we've got Ann Hanks that I'm sure you've seen many times. Jonathan Hanna. We've got Dan Burns, Waqas Saeed, and John Hanks, Brett Sackett. We have a whole complement of great people today showing you some wonderful demonstrations. And we might as well just kick it off. Let's not waste any time because we've got a lot to show you. JJ, what are you going to show us today?
Well, we're going to start with the ripple tank, JP. And so this is a PASCO staple, product when you're teaching about waves.
Does anybody teach about waves?
Absolutely. I certainly hope so.
Right, because it's a very big topic. So, JJ, I'm going to let you have the camera and the floor. I want you to show those fine folks everything you know about the ripple tank.
Thanks, JP. Appreciate it. So, like I said, this is the PASCO ripple tank. It's gone through some evolutions through the years. It's been around for some time. This is the most recent evolution. It's a little bit smaller, which is nice because it's compact, but it has a lot of really neat features when it comes to demonstrating waves, wave patterns, wave interference, reflection, refraction, and I'll show you all that in just a second. But before I turn this on and get the waves going, I just want to go over a couple of the things, the features that you see here. This is an LED light source, right? And so this light source is different than our old light source, which was a halogen bulb that was mechanically strobed. This is electronically strobed. And it's done so through this ripple generator box right here. And this ripple generator box has two arms that hold the actuators that we can use to create ripples in this water. Now I'm going to go to the tank here for a split second and then go back to the ripple generator. This tank that you see here, this square, has about 8 millimeters of water in it. Now some people might think that this area underneath here has water in it, but it does not. In fact, if I drop this is a viewing screen that we're going to use to help. You'll see here that there is nothing there. It's just a mirror right here. And so we've got a tank with about 8 millimeters of water in it. And around the edge are foam barriers, angled foam barriers, and we've added a little bit of a surfactant that comes with it to help reduce surface tension in those areas. And what that does is we're gonna ripple the water. We're going to agitate the water using different pieces that I'll talk about in a second, and those waves will propagate across the tank. And what we don't want is them bouncing back all over the place, right? Because then we're going to get interference in our patterns that we're trying to demonstrate. And so those foam barriers help do that, and they're angled in such a way that will help reduce that. And so underneath here, this is just a mirror and a viewing screen. This is just a diffusing screen, right? And we could take this off, and the waves that we see will actually be projected down onto the table surface underneath us if we want. But in this case, we're going to use this in its sort of demo format, where now we're going to project those waves onto this diffusing screen here, and you'll be able to see them in a second. The ripple generator, back to the ripple generator, it has like I said, these two arms here, the old actuators, and we can have them in phase or out of phase if we wanted to, right? And both are useful tools when demonstrating waves. We can control the frequency, right? And the actuator arms are at the same frequency. We can't change the frequency of the two different arms. The amplitude of the displacement. These red knobs help us control the tilt here because we want whatever actuators touching the water to be flat, right? We want them to be evenly in the water, creating the same agitation. And then there's also a delta function here, and this knob allows us to change the strobing frequency compared to the driving frequency, which will give the effect of waves moving either forward or backward, slower when the delta is smaller, faster when the delta is larger. And we have the ability to have the strobe on, right? The light on at a steady state, or we can have it on at a strobe. So I'm going to turn this on right here. And so right now the light is strobing, right? You can probably see it in my hands here. Now we've got a lot of floodlights going on here that we're going to turn off in a second to help see this, right? But this actuator, this long, thin line actuator arm that's down in the water is creating these waves, and you can probably kind of see them there, but you'll see them better in just a second when we turn the lights off. So along with this system, we also have a bunch of components that we can use to help do the demos that we're interested in. And so right now, on these arms, the actuator is a long, straight piece of plastic, and it creates these plane waves. But we have the ability to change that to, something like a circular actuator or a larger circular actuator. Thanks, JP.
Sure, you're welcome.
Or even a smaller circular actuator that we can use to do things like a point source, which I'll show you in just a second. And then there's also barriers in there. And so these are barriers that we'll use to demonstrate reflection, right? And we'll also use them to demonstrate things like diffraction and interference. And so one of the most important things with this tank is you want to make sure it's level. So a level is handy to have with you. It doesn't come with the system, but you want to make sure that it is in fact level. And so what I'm going to do is I'm going to adjust the frequency. When I turn this on, that actuator arm is vibrating at 20 times per second. I'm going to turn this up to 30. Now I can adjust slower or faster, lower or higher frequency, but I'm going to 30 because the cameras use a 30 frames per second. The frame rate is about 30 frames per second. Otherwise you get this weird blackening across the screen, so we'll use 30. But some of the demonstrations that I'm going to do are better done at lower frequencies or higher frequencies, and I'll talk about that in a second. John, do you mind killing the lights? And I'm going to turn these big strobes off. And so you can see on this projection screen how the waves look. And I'm going to just make sure the front of that arm is nice and smooth. There's not a lot of odd surface tension there. That will give us the best plane waves. And I can turn the amplitude down just a little bit, or I can turn it up, right? But the higher the amplitude, the more distortion you get at the wave generation site. But here's our plane wave, right? And you can see if I adjust the delta here, let me go this way. So now the strobe frequency and the driving frequency have a small delta between them, and it looks like the waves are traveling from left to right. Okay, but I'm going to turn that off because I think it looks better on the camera with the frame rate with the delta off. Okay, and so the first thing that we want to show is reflection. So we've got waves. These could be sound waves, right? These could be light waves with a plane wavefront, right? How does that interact when it reaches a surface, an angled flat surface like this, right? And so you can see here, those plane waves come in, they interact with the surface, and they are reflected. There are lines now, horizontal lines instead of vertical lines. And that is the reflection of those plane waves as they interact with that surface. So I'm going to turn the delta on for just a split second. And you can see how the incoming waves move left to right, and the reflected waves move top to bottom. Let me go back now. And so we can do things like reflection, demonstrate what happens to the waves. And I should have described first, you'll see here there are light areas and dark areas in the plane waves. These represent areas of, for a sound wave, it would be something like a compression versus a rarefaction, right? The difference in amplitude, or difference in the position of the wave, but the the wavelength of the wave would be something from like crest to crest or trough to trough. Right? And we could, if we wanted to, use a ruler to measure that. So there's a flat surface reflection. Now we can do things like a curved surface reflection. And so you can see here, those plane waves come in and they're reflected and they come back and they end up at this focal point right here. And you can see the focal point of this mirror, right? And so let me turn the amplitude up just a little bit, maybe get them a little bit deeper. See, and you can see, I get a little bit of distortion here. Just move this. But you can see that focal point right there. Now, what I want to demonstrate is refraction. And so we've got these waves going through this medium, right? But if we introduce a new medium for these waves to travel through, right, which is represented by this yellow piece of plastic here, you can see that the wave speed changes as they come in here and cross the top of this plastic medium here. And what's really happening is the water has gone from 8 millimeters to about maybe 1 or 2 millimeters across the top. But this is effectively showing how the wave speed changes as it goes from one medium to another. And you can see here the waves come in relatively flat and then they kind of bend in the middle. They slow down. And so I'm going to take this out of here and replace this rhomboid thing with what looks like a plano convex lens. And with this lens in place, you can see here that the waves get bent and there's a focal point out here. It's off the screen, you can't really see it. Let me turn this up a little bit. And you can see that they get bent and you can almost see the lines they form out here. And so this would be demonstrating how these plane waves bend through something like a lens. Turn that down again. And so that's refraction. We can also do things like diffraction. And so what happens to a plane wavefront when it reaches a small slit, relatively small? You get these plane wavefronts regenerating at that slit area, right? Huygens principle. So let me turn the amplitude up just a little bit. So you can see those waves are plane, they're flat, they have a flat wavefront, and when they reach that slit, they start to bend, more so around the edges, right? And so if we make the slit smaller, the effect should be a little bit more dramatic. And you can see that they're much more curved. That wavefront has gone from a flat wavefront, plane wavefront, to a curved wavefront as it goes through that slit. Let me turn the amplitude up just a little bit more. We can probably see it better. Right, and so you've got this circular wavefront, right, coming through. And we can increase this size of the slit, and you can see things like single slit diffraction. And so on the right side of these slits, or the slit right here, you can see areas of the wave canceling out where you have zero amplitude when it reaches the far right side, and areas where it doesn't, right? So we're demonstrating now single slit diffraction. Turn it down just a little bit there. We can see it a little bit better there. But wait, there's more. We can demonstrate a double slit experiment, an interference, diffraction and interference with this ripple tank. And so now we've got two slits, and you can see the plane wavefront coming in and the two circular wavefronts coming out. And let me turn this up a little bit so we can see it better. And you can see the interference of the two to the right of that barrier. And let me I'm going to actually move these a little bit closer. And every time I touch the water, it creates disturbance, which needs to settle out a little bit. So I'm going to let that settle out. And there you can see the two circular waves being emitted from those slits. And you can see the interference as those two circular wavefronts cross each other. And you can follow those areas to determine where your areas on the far right side of the tank are experiencing constructive versus destructive interference. Right? And so this demonstration is one of those demonstrations that's usually done at a lower frequency. So I would have not do this at 30 hertz, but for the purpose of the camera, we have it at 30 hertz. But you would turn it down and you would be able to see a little bit more clearly what's going on. So yeah, there's a qualifier for some of these demonstrations. And so there we've got double slit interference. And if you wanted to maybe demonstrate that, the two source interference, rather than using the double slit example, you can use these point source actuators. Let me turn this down. So we're using a plane wave actuator right now, right? But if I wanted to, I could take this off and put on these point source actuators, and the point source actuators are just two little, basically round feet that touch the surface of the water. And so let me put one on here. I want to make sure they're the same height, and then I'm going to use this gimbal mount to get them down on touching the water. There we go. And so we've got two, move that out just a little bit there. We've got two point sources. And so right now they're in phase. Let me turn them up a little bit so we get the depth of contrast a little bit higher. And you can see clearly the areas of constructive interference versus destructive interference, where the bright line crosses the dark line, right? We've got destructive interference. If you've got a bright line crossing a bright line, you've got constructive interference. Dark crossing a dark, you've also got constructive interference. And so this is a really neat way to demonstrate that this is a real thing. And let me turn the delta on so you can see them being emitted and moving left to right. And you can see the point source actuators going from bright to dark. And if I switch the phase, now one is bright and one is dark. So we've introduced a 180-degree phase difference between them. And so this ripple tank can do some amazing, amazing demonstrations. Let me turn the delta off, put them back in phase. And so the last thing that I wanted to show with this is not only does this work well for wave propagation and wave interference, you can use this setup to demonstrate the Doppler effect as well, which is really cool. And a lot of people don't know that this tool can be used for that. If I take off one of these actuators, I have a single point source here, right? And so the frequency of wave that's being generated is constant. It's fixed. It's 30 hertz, right? And the wavelength all around that generation source is the same. But if I move this, if I slide this around on the table, you can see this odd shifting. It just doesn't feel right. It's almost like a sloshing of water in a tank. That's because the wavelength in front of and behind that point source is actually changing depending on which direction it's traveling, right? So if we move it, if I go, it'll be from top to bottom for you. If I go top to bottom, you'll see the wavelength below the point source is shrinking. The frequency isn't changing, and this can be difficult for students, right? The frequency the wave that's being generated is the same frequency, right? But the wavelength is changing as we move it. And that is the Doppler effect.
Hooray!
Yeah. Well, somebody want to get the lights for me? Whoa! There it is.
Careful what you ask.
Yeah. So that's the ripple tank. It does a million things, and when it comes to waves, if you can think of it, this system can probably do it in terms of application and demonstration. And I should point out, this was all demonstration, but This image that you were seeing here can be projected to the surface of the table, and there the system comes with a ruler that you can use to actually make quantitative measurements, things like wavelength, frequency changes.
You know what I really love about this, JJ, is it's kind of like the new generation in its development. When I was teaching physics, our ripple tanks were huge. They took gallons of water.
Yeah.
The machine was loud.
Yeah.
It made a lot of sloshing. We're only looking at a tiny amount of water here.
Oh, yeah.
We're looking at a device that settles out easily. I can't even hear this one.
No,
and
it makes
it's
zero
running.
noise.
So we've really completely changed the way that we can show some very nice wave functionality without the big setup problems
Yeah.
and all the water and the big messes. I say that for Dan Burns, who told us today that once he set them up, it was so messy and there was so much water, but we're only looking at a little bit of water.
Oh yeah,
so
this
you're absolutely right, Dan.
This beaker comes with the system. It doesn't even fill this beaker up with water. And drainage is easy. It comes with a drainage tube in the corner. You just open the valve and it drains.
Love it. Excellent. Thank you, JJ. That was a great demonstration, a wonderful demonstration. The ripple tank and all the great things that you can do with waves in the ripple tank. So, coming up next, one of our favorites right here at PASCO, our own Ann Hanks, is going to be demonstrating some high road, low road opportunities to take a look at some dynamics. So, we will be moving this device out. Carefully moving this device out and rolling the next card in.
Oops.
Excellent.
I thought I was supposed to get yours.
Either one. Which microphone would you like? You can have them all, actually. And so Ann Hanks is getting set up here. Really a great device. You've seen this device. A lot of you have used it. And Ann is going to demonstrate it at its highest capability. All the great things you can do, taking a look at dynamics, the motion, and the great things that you're able to measure with it. And Ann, you also have a second demonstration that you're going to do, which I'm not even going to try and pronounce.
Okay, that's okay. I'll catch
You're going to
it.
pronounce that for
Yeah,
us?
yeah.
Excellent. Okay. Ann, what are you going to do for us today?
So this is the classic question. We have two carts that are going to start at the same place over here. And one is going to take the high road, which is the short way, and the other is going to take this longer way down and back up. And the question is, who gets there first? So you could think, you know, that since this is so much shorter, that this one is going to win. Let's see. I'm going to put the yellow one here and the red one here.
So we have an opportunity to get your bets in. Those of you betting at home,
Yes.
is it going to be the red or the yellow?
Yeah, and you could argue then that this shorter one is going to get there first, but this one's going to pick up speed as it goes down the hill. So this one's going to go a lot faster. And it's possible that the extra speed will compensate for the fact that it has to go further. So maybe they'll be the same. Let's see. Well, the red one wins by a long shot.
So for those of you who bet on the red,
Yeah.
absolutely.
Okay, so it got going a lot faster than the yellow. Yeah, let me turn these back. So I'm going to. Next thing I want to ask is, if the red one got going so fast, what is the final speed up here of the red cart and the yellow cart? Is the red cart going faster than the yellow cart? And I have my laptop here, which is connected to my wireless smart gate.
Hold on 1 second. Your microphone has dropped.
Oh, sorry. So The wireless smart gate's kind of convenient here because you don't have to have any wires coming off of it. I've connected here, and I have the high road speed showing at the top and the low road speed showing at the bottom. And another way of doing this is using a smart timer with regular photogate. And this is very convenient for the students because it's portable, it doesn't need it to be plugged in, and it gives you the speeds as well. So that's a different way of doing it. So let's see, which one is fastest? Let me push record so that we get the answer. I can't see. There, it's recording.
Anytime?
Yep. Okay, so you see that the high road speed, the yellow car's speed, is 1.3, and the low road is only 0.9. Now really, they should be the same, because if you look at this from an energy point of view, somebody give me a marker. It's right behind you. That's the nice thing about the roller coaster is that you can ride on the board. So we're starting both of them at the same point right here. And then they take different paths, but they end up at the same level over here. And so the difference in height should determine how much faster it's going, because it loses potential energy and gains kinetic energy. So in theory, this should be the same speed, but they're not, because theory doesn't apply to friction in this case. The energy really isn't conserved here. The cart that's going down here and back up is encountering a lot more friction than the one that goes straight down. So in the end, even though it's the winner, it has the lower speed. So, second thing I want to show you is just get this, turn this around here. Is that good? No. So this is the Brachistochrone. We could have had this one set up as well, but Brachistochrone actually means the fastest time. This is a particular curve that we've put into the board so that it will go faster than going straight down. It'll go faster than something dipping down and back up. It is the fastest.
Least time.
Yeah, the least time. I guess that's a better word. Yes, much better. Least time. But what people don't seem to realize is that Brachistochrone also means that it takes the same amount of time no matter where you start. So John's going to start the carts out at different heights on this. And the bottom of the Brachistochrone is right here. The rest of this is just so we can catch the carts. So about right where the split is in the board here is where the two carts end.
So how can should we tip it a little more so that
Yeah,
I can
how's
get out
that?
of the picture? Am I out of the picture?
It's working.
And of course, I can start this anywhere I want. The higher you start, the harder it is to let it go. And you have to make sure that it's on the track right. But is that good enough? Should we go?
Yeah. Okay.
All right, I'm going to let him go. Here we go.
Now that's probably pretty hard to see because it's moving so fast, but both carts past this point at the same time. And you got a slow-mo of it? And it's really neat that no matter where we start on this track, they'll still come down here the same, because the one car doesn't have as far to go, but it doesn't get going as fast either. So in this case, because of this particular shape of curve, they match and they both end up coming through at the same time. Okay, thank you.
Sure. And where does that word come from?
I'm sure it's Greek.
Oh, because I've never seen it before. Can you pronounce it again?
Brachistochrone.
And everybody knows that word.
I don't know.
They do now. That's an excellent word. That's an excellent demonstration. Thank you, ladies and gentlemen. Ann Hanks. Joined by John Hanks, the Hanks and Hanks team. Did a great job demonstrating some wonderful aspects that you can take a look at when it comes to motion and dynamic motion. Coming up next, we're talking a lot about different types of energy. JJ did some things with waves, and Ann just showed the different things that happen with motion. But now we're going to take a look at actual conservation of energy. And to show some conservation of energy, we're bringing in our own physics expert, Mr. Jonathan Hanna, former physics teacher, and now going to take some time to show us a little bit about conservation of energy. Jonathan, you about ready to do that? We got to
do some adjustments first.
Okay, what do we bring in?
Well, we're going to be filming over here, so.
Okay. All right, so in just a second, we're going to switch the lights in this direction and get him set up.
This is amazing.
And there we have it, an instant set change, moving from the left to the right and the right to the left here. And there'll be a lot of that today. As I said, we've got several carts coming in and several demonstrations happening. So Jonathan, you are set up over here on this side. What do we have? What are we doing?
Okay, so what do we got here? This is a very neat product that not many people actually know about. A lot of people know about our tracks, but not a lot of people know that our tracks actually curve. What was interesting, I've had this set up in my cubicle all week, and all the passerbyers were coming by looking at it like, what's Jonathan up to? And first question was,
why do you have this track upside down in your office?
Or do you know that you have your track upside down?
Right.
It's just like,
yeah, it doesn't work like that.
Well, yeah, the card. Well, except you have the smart card too. You know that.
Oh, smart card 2 could do that,
plasma
right?
control, right? So we'll talk about why that's upside down in just a moment. But the other question was, someone came by and said, "How did you get your track to bend?" Well, I didn't do anything special. I didn't use heat or anything like that. I don't talk loud enough, huh?
Oh, you do, but they were hearing your footsteps instead of your voice.
Okay. There we go. We'll try that again.
Perfect.
Yeah. So we actually have track curved, as concave and convex. And what's really neat about it is that it works.
We are going to have some difficulty with this.
Yeah. Let's. John. Yeah. Put it right here. Okay. Let's try that. Let's see. Oh boy.
He's great with physics.
Yeah.
He's just not so wonderful when it comes to microphones.
Well, see, that's why I write and don't talk usually. Okay,
that's not going anywhere.
Well, we'll hope
that's
so.
almost attached to your skin at this point.
We'll see what happens there. But yeah, so these tracks, they come together. We have these pieces that just go in so nicely like that. And, you can get a straight piece of track, put them together like that, and then you can just go crazy with it and do something like this. And the
really nice thing with that, Jonathan, is that this all comes apart. It stores very nicely.
Oh, yes, that's the thing I love about it.
A lot of people like our aluminum tracks, which are terrific. But if you're looking for something that saves a little bit of space and is easy to set up and you can do some really neat designs with, then this is the way you go.
I mean,
Jonathan, I'm going to get out of your way
Okay.
here. I'm going to move over here, and I'm going to let you show them how to use this.
Yeah, so I mean, yeah, even if you don't use the curved parts, I mean, just having these nice short pieces of track, it's great for storage. Yeah, so here, what I have set up here is just, you know, to have a track starting up at a higher point and then comes down, it's a little flat, and then it comes back up again. And the point here, what I'm kind of trying to demonstrate today, is about conservation of energy. And as you can see, I came dressed for the occasion. You can see, got the back as well. So what I'm going to do here to demonstrate conservation of energy is I have a smart cart, and I also have a motion sensor on top of the smart cart. Now, the smart cart's going to measure the velocity, so we can measure the kinetic energy. And then the motion sensor is going to measure the height, hence why I have this track upside down. So the signal from the motion sensor is going to bounce off the track and come back to measure the height. You don't necessarily need to use a track like this. You know, if you could I actually first tried this by going under the table, but that didn't look so well on camera. So, and you could also, if you have a flat ceiling, you could do that as well if your ceiling's not too high. But for this case, I just use track, and that works pretty well. And so let's take a look on the computer. Let me set this up over here for a moment. Okay, there we go. And I'm going to get out of the way here. Oops, no, not yet. These carts have a mind of their own sometimes. There we go. Okay, let me move this out of the way. So I'm not sure if you can see my screen right now, but I have Capstone open, and what I'm going to measure on this screen is just velocity and height simultaneously, and we'll see you know, how they relate to each other. So I'll go ahead and get this started. Okay, so let's take a look at what we see on for the data. So you can see the velocity is in blue. So as it goes down the track, as time goes on, the speed increases, and then once it gets to the most lowest point, we see that it's constant at that point, and then it goes back up here, and then we have another constant section where it's flat over there. And we can also see with the height, they look kind of almost like a mirror reflection of each other. And one strange thing, though, is that we have these little bumps that are around 1.6 seconds and about 2.1 seconds. And that seems to be when it's going along the curved section. I'm not 100% sure what is causing those bumps. I've been trying to work that out all week. I thought it might have something to do with flexing in the track. Interestingly, the bumps don't occur when I take the motion sensor off, so I don't know if there's some rotational thing going on here. But if you have any ideas, maybe you can leave them in the comments and you can help me out. So we can see velocity and height in this graph on Capstone. So what's the relationship between the two? So what if we graph velocity versus height? What will we see there? So let's take a look at the screen at this point. So there's velocity on the vertical axis and height on the horizontal axis. Not quite a linear relationship there. So I guess it's not velocity versus height. I mean, in order to get a linear relationship, I wonder what I need to do to one of those variables. I can't always, I never can remember this. Oh, of course. Square. See, that's why you need this shirt. You got to remind yourself.
That's a very handy device.
Oh, it is, yeah.
Whenever you don't remember what it is you're teaching today, just wear it.
Exactly. So Capstone has this really cool feature called Quick Calcs. So you can just quickly change the calculation of one of the variables. So you can see here I got v squared and I can't see it on my screen. Let's see, v cubed, square root of v. Let's try v squared, since it's on the shirt. And that's a pretty nice linear relationship. Not perfect, but close enough. Now, let's take a look at the energy. So we don't measure energy. I mean, this is not an energy sensor. It's we have a velocity sensor. Well, actually, it's more of a position sensor, but you get the point. But what we can do in Capstone is we can do calculations. So I opened up the calculator in Capstone. I've already entered in the mass previously, measured that earlier today. And you can see, actually, you can see my calculation for the height on line 2, which I just did in inverse of the position, not inverse, negative. And here on line 3, we got kinetic energy, so 1/2 times the mass times velocity squared. And of course, the potential energy, where we have the mass times the acceleration due to gravity and multiplied by the height. And then on line 5, I have the total mechanical energy, adding kinetic energy and potential energy. So let's see how those graph out. Let me get this out of the way. So you can see on the graph, we have kinetic energy in green, potential energy in pink, and then total mechanical energy in blue. And what you notice here, you notice that as the kinetic energy is increasing, the potential energy is decreasing. And during the whole time, pretty much the whole time, except for those 2 bumps, the total mechanical energy is staying the same. It's conserved. So I think this is, I mean, there's many ways you can do conservation of energy experiments. I think this is just another fun way that you can do it. And one nice thing is we actually do have a complete set that we sell. I think it's called the Smart Cart curved track system, that you can build this entire thing, this part on the bottom, with that system. It also comes with the stands as well. Comes with a smart cart. Doesn't come with a motion sensor, but or this top track. But these other things, yeah, there's a lot of other things you could do with that. You can do a potential well. You can make all sorts of configurations. So there you go.
Mr. Jonathan Hanna, and great demonstrations with conservation of energy. And Jonathan, by chance, if I wanted to get that shirt, am I able to get that shirt? Not the one that you're wearing.
Not the one that I'm wearing.
Right. Where might I be able to, Brett, can people order this shirt? This is really a neat thing. Are people... workshop at AAPT. Oh, great
so
shirt.
This is, not many of these out there. So I don't know, maybe check eBay in a few hours, maybe.
And put it up there.
Yeah.
Right. Well, that's an awesome shirt. Excellent. Thank you, Jonathan Hanna, for doing that. We are now going to flip the cameras again. We'll hold on to your seats.
Scene change.
And we're back to set number 2.
I feel like we need some music.
And it looks like we are doing some more demonstrations with motion. And of course, we've taken a look at carts, we take a look at waves. We've seen J.J. Plank and Jonathan Hanna doing some different things. We're going to bring J.J. Plank back in, always bringing you back in for something exciting. J.J., you've got some neat things set up again. Are we doing things with motion?
We are. Well, yes. We're going to talk about rotational inertia.
Oh, well, that's definitely some type of motion, isn't it?
Yeah.
And
well,
is this going to be another fun demonstration that takes a very complicated topic like rotational inertia, which might be almost impossible to teach, and make it something simple to teach?
Yes.
Yes. Microphone trouble all day today. What is it with physics people and microphones?
Just not used to it.
Not used to it, right. They're more used to demonstrating than they are speaking. And so, hook it to your collar.
Hook it to my collar?
Yeah. Excellent.
Yeah.
And remember, guys, if you've got questions, that's perfect. We can even hear your heart beating now. If you've got any questions, write them in. And if you've got a shout out and a hello, we'd love to hear from you. Janet is saying hi back. Do we have anybody shouting out by chance, saying hello? Oh, we've got some great people in Miami, Janet says. Terrific. And we look forward to hearing from a whole bunch of folks across the nation. You say hi. Excuse me? Indonesia is shouting out. Excellent. Nice of you to join us today. Miami to Indonesia and all the way back here to California, where J.J. Plank is going to do some rotational inertia.
That's right.
Let's see it.
All right. So this is probably one of my most favorite engagements with students in class because you pose the question and you just see their, minds exploding, sort of face-melting demonstrations. And it has to do with rotational inertia.
Just a disclosure, we don't do any explosions or face melting or endorse that type of action in the classroom.
And so what I'm going to be doing are demos that use our rotational inertia set as well as our spherical mass set and our standard density set. And so these components, everything that's on this blue box are PASCO products. There should be one more sphere here, but we don't need it. It's the same size as one of these. These are all pieces of scrap material and a giant ball bearing that I found out in our machine shop that we'll also use, but you don't need these. I'm going to add these for emphasis. And so the first question that I ask students is, I've got these two cylinders, right? They're two metal cylinders. This one in my left hand, your right, is brass, and this one in my right hand, your left, is aluminum. They are the exact same size, right? Same length, same diameter. These cylinders just have a different mass, right? And so if I put them on this ramp, and this ramp is not exactly flat, I would have hoped that this thing would have been perfectly flat, but it's got a little bit of a bow to it, but that's no big deal. So I've got these two cylinders on this ramp, right? When I remove that stay and they start rolling, which one is going to win the race? Which one's going to hit the bottom first? Who wants to take a guess? Janet, which one do you think is going to reach the bottom first? The aluminum or the brass? Heavier or lighter? Heavier? Okay, all right. So we get that a lot, right? The brass is heavier. When I remove this, it's going to roll down, probably less effect from friction, maybe gravity's acting on it a little bit more. Let's go ahead and test it. We're scientists, that's what we do. So 3, 2, 1. And they reach the bottom at the exact same time. May not have been exactly the same time, but just about the same time, right? So mass, does it affect this race? No, it doesn't. In fact, we could have gone further. There's a third cylinder that's plastic. It's even lower mass. We could have had the race again, and sure enough, they would have reached the bottom at the exact same time.
JJ, you didn't give that option to Janet. You said which one goes first. You didn't give her the option of saying the same time.
Ah.
It was a trick question. That wasn't nice. That was not nice.
Okay, I'm sorry. And so now what we're going to do is I'm going to take a new cylinder that has a larger diameter, right? And so we're going to ask the question again. Janet, maybe we'll ask Nolan this time. Nolan, which one of these is going to win the race? The larger diameter or the smaller diameter?
The larger diameter.
Larger diameter? Okay. So we've got the larger diameter, and let me set these up. Let me stage them here. And so I'm going to let them run the race, and we'll see which one wins the race. Whoops. So 3, 2, 1. No effect, right? So diameter has no effect. And we have another, maybe it's the material. Does the type of material affect which one wins the race? 3, 2, 1. Absolutely not. So mass, diameter, the material, which is effectively the mass, right, doesn't affect the race. So now I've got, make sure that one doesn't roll off, I have two cylinders, but this one is a ring instead of a solid cylinder like this, right? Do you think this will affect which one wins the race? JP, which do you think?
Every single time, you end up doing the same thing, and it's always the same answer. They always get there at the same time.
Okay.
So I'm going to say they get there at the same time.
So they get there at the same time. So we've got a ring and a disc, and we've seen them all sort of reach the end at the same time. We're scientists. Let's test this. 3, 2, 1.
Not nice, JJ. Definitely not nice.
JP, your intuition is amazing.
Definitely not nice. Well, what happened here?
Yeah, so we just saw that the ring, right, loses the race, right? So this disc, this solid disc, seems to roll down the ramp faster than the ring does. Well, let's test some other permutations. So we've got and now we tried two discs of different diameter or radius, right? And they reached the bottom at the same time. Now we've got a ring here as well and a disc. Which one do you think is going to win the race?
Janet, which one do you think is going to win the race?
The ring or the disc?
The ring.
The ring, okay? Because it's smaller, right?
Yeah.
So 3, 2, 1.
Yeah, this is so counterintuitive. This isn't what anybody would think it would be. This is a really exciting demonstration because it's constantly challenging what I want to believe.
Yeah, so clearly this ring loses the race, right? But you know what? There's something else that we haven't tested yet, and it is the length of the cylinder, right? And so this is not part of the set, but I just happen to have these. So I've got two cylinders, same diameter. The masses are different, but we already showed that mass doesn't affect it, right? So do we think the length of the cylinders will affect it? Now for this one, I'm going to need to use this meter stick. And you might want to watch your toes.
Right, yeah, I'll watch that.
So we've got two cylinders. Do that. 3, 2, 1. Ooh, now it looked like they may have reached the bottom at the same time, but I think that might have been me with this meter stick. Let me try that again. I'll do it with two hands. Ready? 3, 2, 1.
Oh yeah, they did not reach at the same time.
So I actually bumped it with the meter stick again. I'm not doing a good job, but these actually reach the bottom at the same time.
Oh, they do?
They do, yeah, because it turns out, because they're solid cylinders, the race will be a tie every time.
So it appears to me that it's a matter of solid versus hollow.
That's exactly
we've
right.
already identified that mass doesn't do it. We've already identified that the size doesn't do it. But this whole solid versus hollow is what's throwing everybody off on their assumptions.
Yeah, that's exactly right. And so even this race.
Okay, so they're
Right.
both solid.
So they're going
to go at the same time.
They'll go at the same time.
All right.
This one is.
Yeah, fool me 3 times, shame on me.
All right, here we go. 3, 2, 1. Right, and so now we can say that these discs, or excuse me, these rings lose the race, right? So what happens if we do both of the rings at the same time?
Right, because they're both hollow.
Yeah.
And we've already identified that mass doesn't affect it, but
They are
hollow,
definitely different mass.
But they're definitely different mass, but mass didn't affect it. They are both hollow. I don't know, JJ, what? No, I have no idea.
Let's be scientists again, and let's go ahead and give this a shot. Ready? 3, 2, 1.
At the same time.
At the same
So
time.
both hollow,
Yep.
different mass. We knew that mass didn't affect it. They were both hollow, even though the hollow, the space in between is different.
Oh yeah, much different. And so it turns out that no matter the length, no matter the diameter, no matter the mass, if you have two rings like this, right, that have the same sort of density or amount of mass thickness on this ring here, they're going to reach the bottom at the same time
Every single time.
Yeah. And the same thing goes for solid discs. They could be different mass, they could be different diameter, they could be different length. They're going to win, they're going to tie every single time. But if you have a mix of a disc and a ring, the ring loses every time.
And why?
It's
so now we say
Yes.
the answer behind why everybody keeps getting this wrong is...
And the reason is, it's because the mass of this object is distributed further from the axis of rotation. So this has mass, let's say uniform density, all the way across from the center all the way to the edge. This one has its mass located at its edge. And so it has, its rotational inertia is affecting its ability to convert potential energy to linear kinetic energy. In fact, it needs to convert more energy, more potential energy per unit mass into rotational kinetic energy.
Because its mass is distributed
Because
to
it's
the outer
further
edges.
from, that's right. And this one has mass all the way across, so it's distributing its potential energy per unit mass, right?
Because it takes less energy to convert that to motion in the center.
Right.
I see.
Yeah, and so this extends beyond disks and rings too. So we did cylinders, but we also have spheres. And so how does a sphere behave in the same way, right? And so the set comes with these two spheres, right?
Are these solid?
These are both solid, yes.
Okay.
Okay, and so, oops, do this the other way. So we've got two solid spheres, right? About to run the race.
And that's what I would expect. After
Yes.
your last demonstration now, recognizing they're both solid, understanding that they both now have to convert the same amount of mass to energy, that they should have arrived at the same time, and they did.
That's right.
And so where you got me the first time, now I'm doing okay. And so I would imagine any of those solid spheres, regardless of the size, are always going to reach at the same time.
That's right. So if they're solid, they're going to reach the bottom at the same time. If they have that same sort of distribution of mass away from that rotational axis, they're going to reach the bottom at the same time. And so now I've got two more spheres.
Uh-huh. They look identical.
They look identical. I'm going to just move them up a little bit higher.
Uh-huh. Okay.
One definitely got there first.
Yeah.
So what do you think?
So what are you doing here? So as I pick them up, they have a different mass.
They do. They
And
certainly do.
one of these is hollow, isn't it?
Yeah.
Okay.
Well, hold on. So they have a different mass.
They do.
Do we have an
We
issue with
already
that?
identified that mass wasn't part of what contributed to the difference in speed.
Yes, and we can galvanize that with students by using, let me put that one in front. Now we've got a solid plastic sphere and a solid metal sphere. Let me start that over. I got to get better at my release. Mass
And they hit at the
has
same
no
time.
effect.
So they're both solid, they hit the same time.
Yes.
Mass has no effect. Even though these two have different masses, they're definitely hitting at a different time. And so you have to reach the conclusion that ball is hollow.
This sphere is certainly hollow. And that is part of the set. And
So every time you try to trick me, but the really nice thing is, JJ, we're going through a progression where you're actually emphasizing the concept, and now I'm able to reach some reasonable conclusions based on what you've been showing, which is really fun.
That's correct. And that is the rotational inertia race. And so, like I said, there's three products. There's the rotational inertia set, the spherical mass set, and this comes with a fourth sphere. This is steel. This one is hollow. There is a solid aluminum and then a solid plastic. And then these come from our density set, and there are 3 cylinders that come with it. A third is a plastic one.
That's awesome. What a great demonstration. Thank you
for
teaching me and everybody at home a little bit about rotational inertia. Awesome. Okay, so coming up, we've got another exciting demonstration. Who do we have coming up for us? This is a favorite. We're looking at the bicycle wheel gyro, and we'll be bringing Dan Burns in for that. And as we're bringing Dan in for that, let me just say that we've had a couple people that have reached out to us, and we want to say hi to. Philip from England. Philip, always nice to hear from you, and certainly nice that you're joining us today. And Shadi from Lebanon is giving us a shout out, and it's nice to have you joining us today, so thank you for that. And any questions that you have so far today for Dan, for Jonathan, for JJ, for Anne, any of the demonstrations that you've seen, write them in. We're here, we're live, we're able to answer these questions for you. Or if you just have a shout out and you want to say hello to us, we are so excited to say hello to you as well. So we are setting up. Dan is pulling some very interesting things both out of the ceiling and off of the wall here. Dan, what are you doing for us here? What's going on?
Well, I have the PASCO bicycle wheel gyro,
Uh-huh.
and there are a lot of things you can do with the bicycle wheel gyro. I'm going to concentrate on what I think is one of the most astounding physics demonstrations that you can do for your students, and this makes it pretty easy.
And this is a staple in every physics classroom, Dan. I don't think I've ever seen a physics teacher not have one of these devices because of its utility of some great concepts to teach.
And hard to explain, some of them. So
Right.
we'll see
Well, I
what
can't
we can
wait to
do
see
here.
what we get.
So what I always do is start off with just having it hanging by the rope here and point out that if I were to let go, it's not going to fall. What's it going to do? It's going to rotate, right? There's a torque from the weight of the wheel about this axis point here that would allow it to rotate. Now, if I spin it, then maybe something different will happen. And I've always spun things by hand, but this comes with this neat little gizmo to get it really spinning fast, which may or may not be a good idea. But in the interest of entertainment, we'll give it a try. So I just wrap it around here, kind of like those little toy gyroscopes. But usually I can get, what?
It's a lawnmower.
Yeah. Yeah. I think I could do better, but it's spinning. I let go now, and the students might say, oh, it didn't fall. Let's give it a little more. That's how I always did it. They would say, oh, it didn't fall. Well, it's rotating just like it did before. It's just rotating in a plane that's 90 degrees from where you may have expected if you've never seen this before. And so sometimes you just end and say, hey, it's, right-hand rule, it's a gyroscope, it's precession is the term for that. But we can actually understand it if we've gone through some basic physics already. So let's do that. So imagine the wheel spinning like this. I'm going to stop it a few times to explain some things, but it's always spinning like this. And I'm going to attach a particle to the wheel here. And if right here as it's spinning, I let go, it would start to rotate toward me. At least it has that tendency, right? Now, the velocity of this particle is in this direction at that point. As it moves, it's still in that direction. In other words, its velocity isn't changing. So it doesn't have an acceleration due to that changing velocity, the momentary direction. So no force is required there, other than the centripetal force to keep it going in a circle. If it's here, then we have something different. As it starts to move, its velocity changes direction. At this instant, so again, remember it's rotating like this. At this instant, its velocity is up, and if it were to rotate 90 degrees, it'd be toward me then. And we know to make something turn like that requires a force perpendicular to the direction of the velocity. So the wheel would have to exert a force on this particle in this direction to make it go like that. The particle, according to Newton's third law, applies an equal and opposite force to the wheel. And so there's a force out on the wheel from the particle. Now if the particle, so here there's a force out. Now if the particle is on this side, and again the wheel's spinning like this, and if the wheel started to go like this, well, what's going to happen now? At this instant, the velocity is down. And if this were to start rotating like this, it would be moving more out towards you. So how would you make something that's has a velocity down, turn out towards you? You'd have to apply a force like this. So the wheel would have to apply an outward force on the particle. Newton's third law, the particle applies an inward force on the wheel. So if we combine that, I had another particle.
It's right up above the camera. Next, yep, right there.
I made them easy to see,
Yeah, they're there.
and I couldn't see it. And so this one, there's a force in on the wheel from the particle. Here there's a force out, so that's a twist. So what we're doing is predicting if the wheel's spinning like this and I let go, then it should twist like that. and that sort of works. And so you can give a explanation. It's not complete, but an explanation that introductory physics students could understand. They may wonder, hey, it's a whole wheel. Well, you could add up effects of particles all along here, which would be less and less and less. So by focusing on these 2 points and the place where there's no effect, you can put that together and get a good picture of this. And so
Awesome,
that's the
Dan.
bicycle wheel gyroscope.
Dan, the thing I really love about what you just did is you took something complicated and you just used Newton's 3 laws to explain it. And one of the things that I know when I was doing things similar with my students, I would say like a force in a direction keeps going in a direction unless acted upon, which is what you just demonstrated very nicely
Right,
with this.
taking what they've already learned to understand something, at least get more understanding about something that's very complex. We'll find out there's more to it, I think, in our next demo.
All right, because we
us.
take it a step further. So
Yeah.
thank you, ladies and gentlemen, Mr. Dan Burns on the bicycle gyroscope, and lots of things moving out of the way here. So we are going to take that a step further because Dan took Newton's 3 laws very simply and a bicycle wheel and put it together so that we had a very nice demonstration. Now, we're going to take that a little bit further. We're going to actually look at precession and nutation, and we've got our folks setting up our set here for our next demonstration. And as we bring that in, of course, we are looking forward to your questions. If you have any questions for Dan Burns, again, we're live, so just get those questions out to us. And looking forward to your shout-outs. Janet, do we have any more shout-outs going out today? Some exciting people?
Greetings from Taiwan.
Greetings from Taiwan. It's nice to have you here. Thank you. And?
Norway and Canada.
Norway. Always nice to hear from our folks in Norway. I bet I can even tell you who that was. I'll take a look, but I bet you we know who our friends are out in Norway, and nice to have them. And Canada is saying hello, so coming across the world and coming in to say hello, and always nice to see our great folks out there. And so setting up now is Wakas, and Wakas is one of our engineers here and a great physics demonstrator. Those of you internationally know Wakas because he joins you all the time, and domestically he is a great assistant when it comes to understanding some of these physics concepts. Wakas, what are you putting together for us today?
This is our 3-axis gyroscope. So we looked at one gyroscope, which is a bicycle wheel. That's a classic example. This is going to be a similar experiment, just different, given that we have it on fixed axes.
So we're taking what Dan just did and we're expanding it a little bit further because we're able to do it and rotating it in a lot of different directions here. This device almost looks dangerous.
It can be. I mean, I got to keep it away from my screen. I don't want it to swing around.
Right, exactly. That thing swing around and knock your computer down.
hit, so.
And I see that we've got a lot of different sensors on here measuring a lot of different things.
Yeah, so I have 3 sensors actually, and traditionally we've shown this setup with rotary motion sensors, but today we have something a little bit new where we're actually using a wireless smart gate, and with that I'm able to, with the 3D printed mount, I'm able to determine or at least measure how fast the disk is rotating. So that's something new that we have today.
Oh, taking an experiment a little bit further.
Taking it one step further, something that we had to sort of just observe before, now we can actually measure.
And if somebody wanted to print that out, they can find the print instructions for that?
The 3D files should be available, if not right now, shortly after this. Yeah, they're available right now, pasco.com/DIY. Go to Thingiverse. You'll find it on Thingiverse. We have a lot of different designs there, and that's where you'll find this too.
Excellent. Well, Wakas, I'll let you get to your demonstration.
All right, thank you. So before I connect any of the sensors, I want to just go over a couple concepts. Actually, I need one more part. Two. So Dan Burns explained how a gyroscope worked, and those same concepts apply to this gyroscope, even though it's not a bicycle wheel. But it's a similar type of thing where we have a rotating wheel that has a mass, it has a momentum on it, and that rotation is going to cause the gyroscope to move in a certain way. Now, what's different here is that if you look at it, if I let this go, my gyroscope, it's not falling forward, you know, like the bicycle wheel on the string, and that's because I have these counterweights. So what that allows me, what these counterweights do is now, it's not the weight of the wheel that's pulling it forward, right? It's, what's going to cause it to drop? Well, a known mass that I can weigh, that's what is going to cause the wheel to fall forward. So now if you look at the equations for measuring the torque and different constants of a gyroscope, you're going to see that one of the things we need to look at is the radius, which is the length from the center to the mass, and the weight of the mass. So in this case, we know the weight of the mass, and the same concept applies where if we if we rotate this disc, then depending on the direction of the rotation, the gyroscope's going to move in one of the directions. So let's do this. I'll rotate this by hand right now, and if I let this go, well, it's not doing much. I mean, it's rotating, but what happened to the the spinning thing like the bicycle wheel? Well, this is where we can prove that we need to, if we add a weight, it starts the precession. And if I rotate the disc the other way, same thing, does nothing. If I add the weight, it starts going the other way. So because we're PASCO and because we are a measurement company, we have wireless sensors that do measurements. We can actually use our rotary motion sensors to determine, well, first of all, we have a rotary motion sensor that can determine the angle of the gyroscope up here. We have one at the bottom that can determine the rotation angle, the rotary rotational angle. And we have the, again, the rotary motion sensor here, and that is determining how fast the disc is turning, just like I explained before. So first I'm going to show you, just with the two measurements of the two angles, show you what the nutations look like. And that's what, when you apply this weight, how the two angles are correlated with the bobbing of the gyroscope and the rotational. So let me go ahead and connect my sensors. All right. You have my screen up on the screen? Yeah. Okay. All right, so I have my sensors connected. I want a graph, but I don't want a graph of angle versus time. I want to just see the relationship between the two angles. So I'm going to create one more graph and just change the axes. So let's do this versus, so the angle at the top versus the angle at the bottom. And if I press start, let me spin the disc again. And watch what happens if I actually, I'm going to spin it one more time a little bit faster. If I apply, so we see that it wants to move that way. What if I just kind of tap it in the wrong direction? Let's try that again with the string so I can actually get this thing going really good. All right. This way it gives you a lot of power over, oops. Okay, stop, start. Now if I just tap it in the opposite direction, it wants to, there we go. Now we see these loops happening because I pushed it in the direction it doesn't want to go, so it's trying to counteract that by, having that reverse movement. And again, with the, I can, now that I can measure that along with observe it. And of course, if we add the other sensor here, we can get the speed of the disc as well. Look at our gyro disc, the gyroscopic equations, and then we can determine, prove all of the effects that we need to prove. Anyways, so there's just a simple demonstration on how our gyroscope works. One other thing I wanted to point out is one of the benefits of using this is that one of the concepts that we see is that the rotary motion or the gyroscope disc is turning. Now, the rotation is what keeps it balanced. What if I stop the rotation? Right away, it drops. So it's not the spinning of the disc itself, it's also the precession that keeps it turning. And by stopping the precession, the disc falls. Not falls, rotates to the ground.
Rotates to the ground. Right. An awesome demonstration, Wakas. Very nicely done. And Wakas, what you're demonstrating here, of course, I know you're showing it very simply, but for those of our folks out there that talk a lot about astronomy, you mentioned precession. We talk about the Earth on its axis undergoing precession.
The Earth does a similar thing, right?
Right, and then you also mentioned nutation, which is also explaining the way that the poles move in their motion due to the spinning of the Earth on its axis. So both of which you're demonstrating here, a nice little thing right here on your desktop, but really a great way to explain what happens with the Earth and its rotation and being able to measure some of those things with it, yeah?
Right.
Yeah, very nicely done. Thank you.
Thank
Awesome.
you.
And so, ladies and gentlemen, we have been through several demonstrations already this morning, and we're getting ready to set up for the next set of demonstrations. But before we do that, we're going to take a break, and you're going to join us as we interview some of our folks here at PASCO and take a look at what makes this company tick as we clean up our set. Are you ready to go to our interview, Nolan?
Thanks for joining us. Can you please introduce yourself?
Hi, my name is Tina Wood.
And what do you do at PASCO?
I am a new product introduction specialist. I help with the new products when they come out. I'm a lead in the assembly area and help training and work with the engineering on some of the new projects for the new boards, prototype boards.
Right. So when we do a prototype board, you're sometimes in there putting some of that together.
Yes.
And that's sometimes a lot of very small components.
Very tiny work, yeah.
So you're kind of like a wizard when it comes to that.
I'm getting better at it.
What do you enjoy most about your job here at PASCO?
Besides the people I work with are great. Variety of work has always been fun. There's always something new every day to work on.
And how does working at PASCO compare to assembling guitar amplifiers at Mesa Boogie?
Oh my goodness, this is much more fun. That was like the same things every day. You built an amplifier, sometimes different variations of it, but yeah, this is a lot more fun.
Right, okay. For that special someone in your life, if you could buy them anything from the PASCO catalog, what would it be?
The arm. The human arm.
The human arm model?
Yeah.
Okay, yeah. Excellent, excellent. Who would win a rap battle? Sir Isaac Newton or Albert Einstein?
Einstein.
Okay, I'll go with that. That's excellent. Thanks for joining us.
Okay, you're welcome.
Good? Good. One take.
Yeah, when it first starts.
And we're back, and that was a pretty exciting interview, and I'm glad that we had the opportunity. We've got a few more of those coming up. You've already been joining us now for 7 great demonstrations. We love the shout-outs. We hear more coming in from Taiwan. We had a shout-out from Hong Kong, so we say hi to our folks out in Hong Kong. We are trying to figure out if it's Glenn or Eric that's saying hi to us from Norway, so we're just going to assume it's both of you and say hi to our friends out in Norway, and glad that you're joining us. And we've got more demonstrations now, so we've cleaned the set, and we've moved Dan Burns back in, and Dan is going to be doing some exciting things from his experience working on the chain gang. Right, Dan?
So I've been doing a lot of experiments with chains. What's neat about it is you can get away from the massless strings and cords and use something that has a significant amount of mass and see how that changes
do some fun
the
stuff
experiment.
With it. Interesting. Okay, well, I'll let you go.
Well, this first one here is dealing with a chain that we are going to drop. And what I want to know is the force on the table from the chain as it falls. And to be able to measure that, instead of on the table, we'll have it land on this force sensor. And so what you want to do is be real careful, have it nice and steady, and to make it simpler, we will assume the chain is just about to hit the force sensor. And so it's not going to fall through a certain amount of height before it hits. And it's still a complex problem, though. So as it's hitting, there's sort of 2 components to the force here to think about. There's the weight of the chain that's resting on it. And then as it falls, the chain is coming to a stop. So the force sensor has to apply an extra force to stop the chain. It's equal to the rate of change of the momentum. And so that's kind of a complex problem.
Dan, let's unplug the HDMI and plug it back in.
Let's give that, that always works, right? Maybe. It's a little, maybe. Kind of lost the whole display. There we go. That'll be coming up soon. I think it's like cycling through 3 different modes there. Well, let's see if that fixes itself. We'll just deal with it. So what you can do is solve this with calculus. Yeah, it is. I think it's my connector. I've got one. Okay, I had a backup one there too. I thought we did test this, but like we had 5 seconds of test.
Anytime you go live with anything, it's going to change a little. Let's see if going to switch out the dongle here and see if we can't get the computer to show what we're seeing here on Dan's computer and see if we can't get that up on the screen. While Dan's hooking that up, it's very interesting just to kind of show the sensors that Dan's using. If you can't see those directly, we're using our standard force sensor, which is neat, but then Dan has this neat little thing on top, which is actually a force sensor balance stand, and it's screwed right into the top of the force sensor, so it turns the force sensor into a device now that is actually able to measure as a balance would. And a really nice little device. These are orderable. Yes, JJ? Yes. This isn't a 3D print thing. This is, you can actually purchase that. Is that part of a kit or is that a standalone?
It's all by itself.
All by itself. So turn your simple force sensors into a simple balance stand that you can do some of these activities with just by using this device. We've tried a different dongle now. Let's see if we're able to see the screen, if it's coming up.
Sort of. And so here's a solution to this using calculus, and in this case we're solving for the rate of change of momentum using an infinitesimal amount dt.
You have extended screen.
Yeah, switch it to your other desktop.
Let's see, that made it work.
I just see your desktop.
There we go.
I just needed to walk in there.
So I'm not going to walk through all that. Actually, I do in a YouTube video, which I have the URL up there, and we might get that into the chat to make it a little bit easier. But you may want to do this even with students that don't use calculus. And so what you can do is just take a finite amount of time and figure out the change in momentum for how much chain falls in that time and add it up. And I'll show you how to do that with our Blockly programming. Now, another thing to make this easier, so JP talked about this different attachment I put onto the force sensor to make it sort of a pan balance. You can also print these out in, with a 3D printer on Thingiverse. We have that. And you could just go to the hardware store and get some bolts and a piece of metal or something and make your own. I use these in my class. To help catch the chain, I'll put a cup on there. So we would zero the force sensor so that we're just measuring the force. And then I just have to hold this chain. It's a 1 meter chain. We know the mass.
Wait.
What? JJ, I'm in the middle of this demo.
That's not a chain, Dan. This is a chain.
Okay, we'll do it your way. But force sensor wouldn't work. So I guess we need our force platform. And we got a bucket. It's almost like I knew he was going to do that. And so we will measure using this chain. And so let's see what that looks like. Now, if we go back to all that calculus stuff, which is kind of, there's a lot on that slide, but at the very end, the final conclusion is the force will reach 3 times the weight of the chain right as it's about to complete its fall. And that's because at the end, we have almost all the weight of the chain on, and it's falling at a faster rate, so a bigger chunk of mass is going faster and needs to be stopped at the end. So that's what we'll look for here in our measurement is, does the final force equal about 3 times, oh, better plug this in, 3 times the weight of the chain, which will be the final force that we measure. There we go. Let's see if it's reading 0. It's reading 0. Got 6 feet of chain, which I think is 1.83 meters. And it's just touching. And it stopped measuring for some reason. Well, I know why. Do it again. Gotta be faster. I put in the Blockly code. Got it. Sorta. So the maximum force here was about 45 newtons. And if I measure the weight of the chain now, it's about 16 newtons. And so that's about 3 times 16, 48 newtons. So pretty close. Now I mentioned doing this without calculus. So here's the Blockly code that would accomplish that. We were just solving for how much weight is already fallen onto the force platform, what the force is to stop a little piece of chain coming in that amount of time, and then we add those two together, and then we increment, hey, how fast is the chain falling now? How far is it falling? And we keep doing that, and we output our prediction for the force. And so now this is output from the code.
And this is really neat, Dan. What you're doing is you're using the Blockly coding that's built into the software. This is built into it, and you've now made a model, a predictive model using the code. And then we could actually go back and now test that predictive model with the real thing.
Ideally, you do the prediction first, but just for this presentation, I thought we'd go the other way. And you can see that the maximum force here is about 47 newtons. And so this is predicting,
and that's predicting
the same
exactly
thing that
what we came up
calculus
with.
did. So,
Right.
so that simple code replaced all that stuff. And so you might say, hey, what if I have kids with calculus? I think they understand the calculus better if they also see this sort of finite time step approach, and they get more of an understanding of what it means to take an infinitesimal amount of time. And so, a complete write-up of this even links to a sample lesson and lab for dropping the little chain. Sorry, JJ, because you probably have access to more force sensors, is at that YouTube link. And you can find out more there, and always feel free to contact me.
And the nice thing is, Dan, you could have done the little chain or the big chain, both with the predictive model, and come up with the same conclusion.
And I think we have more about chains. I just need a minute to go grab a little bit more stuff here.
Okay.
So you can entertain the folks.
Sure, yeah, I'm all here for the entertainment. Thanks, Dan. And so I'll just fill some time, ladies and gentlemen. Dan Burns. Do we have any good shout-outs coming in, Janet, from anybody great from our international crew out there? They are all great. That's right. We've got some new folks coming in, more folks coming in from Taiwan, I see. Really, so great to have you with us. Who else, Janet?
Glenn says hello. He is Norway representing.
Ah, so it's Glenn from Norway. That's so nice to have you with us, Glenn. Awesome. And we've got a lot of our domestic folks coming in, too. I see we've got some folks joining us from different states around the United States. It's nice to have you here. And for all of you, if you've been watching the news, you probably know that California is on fire. It seems to be what we do every year, and we're doing it really well this year. And so everybody is safe here. The fires are actually not that far away, and it's actually a very scary year with fires, and there's a tremendous amount of smoke in the air, but we're safe here. Everybody is safe at PASCO, and we're all doing well, but we are watching the fires very closely, and we really appreciate you reaching out and saying hello and all of your concerns, but we're safe, and thank you for asking. Dan, we grabbed some more stuff. What are you ready to show us now?
What do I do with my chain?
The little one
Yeah.
is right here?
Well, that was, yeah, of course, it fell on the floor.
It's on the floor, right.
So now we're going to look at a Atwood machine problem. And to make it a little simpler, we're going to not have masses on the string, or in this case, the chain. But again, we have a chain, so it's not a massless string. And what we're going to do is put it on our wireless rotary motion sensor. And we can measure the linear, well, we could also measure the angular quantities, but we're going to measure the linear speed of the chain as it falls and its linear position. And to predict this, again, you could use calculus. Here's a slide going through it. I'd say this is a little more complicated. This one is also allowing for, let's see, no, this one I did simplify. It's just chain. And so a lot of stuff there. Your calculus students should be able to handle this. But again, the final solution is pretty neat. We find that the speed of the chain is directly proportional to its displacement, x. And the slope of that would be the square root of 2g over L. So the mass of the chain doesn't matter. Now, you might be wondering, hey, could we also predict this using that approach with Blockley? And the answer is yes. So we also have a Blockley code, whereas this thing rotates, we just keep solving for how much mass was added on this side, which is pulling this way, and then how much mass was lost here, same amount, right? And then we calculate the new net force on the system. So as the chain goes, the new net force keeps increasing. And instead of solving that in closed form like we would with calculus, we can just numerically solve for it and make our prediction as well. But first, let's measure it and see what that looks like. See if it is linear as we predicted. Now, it matters how much is on one side versus another at the start. And so in this case, we're assuming it's balanced with just a tiny, tiny bit on this side, or let's see, the other side. We want it to go positive, measured with this as counterclockwise from your perspective. So I'll hit start or record and just give it a little bit to the other side. And we got our graph. And you can see it was linear. Here something interesting happens. I've watched it in slow-mo. The chain starts to come off the pulley because there's not enough force to hold it there, where you don't have enough force toward the center from the weight of the chain to make it spin in a circle. So that's a whole other program we'll do later. But it's certainly linear here. And if we measure the slope of that using capstone, we get 4.11. So how does that compare to the theoretical? I think I put it in here. When I did this earlier, I got 4.16. Theoretical for a 1 meter long chain is 4.43 seconds. 1 over seconds would be the units of the slope. Now let's see what the Blockley did. Well, let's watch it. I'll redo it again. And so the Blockley is generating the velocity versus position data from our program. And we're getting the slope. It starts out a little non-linear, but definitely linear for the bulk of that. And the slope predicted by Blockley is 4.46, whereas calculus is predicting 4.43. I could change the time step and it would get a little bit better. So you can have students model a complex system with Blockley without knowing calculus. You can have calculus students do the model, and then they understand it better. I think they understand what they're doing with their calculus better.
What the calculus put in there. And the neat thing about what you did with the modeling, Dan, is that you use Blockley, which tends to be a lot of people refer to it as a simple form of coding, but it's not really simple when you can see some of the more complicated things that you're able to model.
All the same ideas and concepts in any kind of code are all there. And the visual nature of it makes it kind of a low bar for students who are unfamiliar with coding, in my view.
Right, and so you could probably spend a lot of time doing the same thing as something like Python, but get hung up on syntax. Here we're able to assemble a very nice program that models very nicely, does a very good predictive model, and we don't have to get hung up so much on the programming. We can focus more on the physics.
And if you want to try this in your class, I have another video that goes over a lot of details and links to materials and slides and a sample lab handout. This URL, and I'm sure Janet is getting that in the chat, so you can just copy and paste, give it a look, and then if you have questions or want to tell me how it went, dburns@pasco.com.
dburns@pasco.com. Ladies and gentlemen, Mr. Dan Burns with another great demonstration. Now, we're going to be moving Dan off of this set, and that's great, but we'll be seeing Dan a little bit later because Dan's going to do something right here in our own studio. He's going to be demonstrating a supernova, which isn't something folks are usually able to do in their studio, right?
Safety glasses.
Get your safety glasses, get your sunglasses. We'll be doing a supernova, and we'll be moving this set out. We're really very excited to have all of our folks joining us in all of these sessions. So far, we've heard from Taiwan, we've heard from Hong Kong, we've heard from Norway. I'm waiting for our shout-outs from our good friends in both Central and South America. ¿Qué pasa? ¿Dónde está? We always hear from you, so I'm looking forward to hearing from you very shortly and tell us that you're joining us here. Coming up, you've probably wondered, what are some of the really neat and wonderful things you can do with a meter stick? Well, I got to tell you, it's a never-ending list of great things you can do with a meter stick, and we actually start by taking a look at some of the neater devices that are being assembled and demonstrated. And we're going to bring Ann Hanks back, and she is going to be using the meter stick to demonstrate something very interesting, meter stick torque. And so, ladies and gentlemen, Ann Hanks is back with us. Thank you. Did we get a shout out from Central or South America, Janet? Anybody with us yet? We're waiting for you. We're hoping to hear from you. We know you're watching, so we're looking forward to hearing from you very shortly. will be turning this device on, and Ann Hanks will be demonstrating. And for those of you who haven't seen the brand new meter stick, what a neat new device. Now purely aluminum, nice and hollow, lightweight, doesn't bend, doesn't break, can't chip it, and I'm in your way, right? Just say get out of the way. And Ann Hanks, ladies and gentlemen.
So this is our new meter stick torque setup. Uses our fabulous new hollow aluminum meter stick, which is just super cool. You have to feel it to believe it. We all carry these around all the time here because it's just fun to have in your hand. It has good rotational inertia.
As a simple hand demonstration.
Yes.
Right?
Mm-hmm. So in this case, though, I'm using our new meter stick torque apparatus, which takes the classical meter stick torque, which just was a pivot and some little hangers, and classes it up a little bit because we have actually a ball bearing pivot here. So this pivot is new. It looks a little bit like a rotary motion sensor, but it doesn't have any internal electronics. Yeah, it doesn't have any encoder or anything in it. It's purely a pivot. In fact, I call it bearings on a stick because you can stick it on anything and just use it for its bearings. In this case, we have it hooked up with the little meter stick holder that allows you to slide the meter stick back and forth through it. This has the unique feature of having a level on it. And in this case, I really need the level because I'm trying to make this meter stick level in my experiment just to make things easier to calculate. So I've got a hanging sign over here, 200 grams hanging on here. The mass hangers are exactly 10 grams. So we made them an even number so that they're easy to add into your experiment. So if this is an equilibrium, then the sum of all the forces equals 0, and the sum of all the torques equals 0. And I want to show you how we can get the mass of the meter stick from this. I know approximately what it is, but we'll see how it comes out in the calculation. So I've got this pushing down on here. Notice that this string is pulling up on the meter stick and causing a clockwise torque in your direction. No, counterclockwise, sorry. I'm backwards. Yeah, so it's a counterclockwise torque for you. Everything else here is causing a clockwise torque. As you can see when I hang this on here, it's pulling it down and counterbalancing that torque. But there's also a couple little hidden torques here. There's the weight of this hanger, which is 10 grams, and times G. And then the meter stick itself has weight, and it acts at its center of mass, which is at 50 centimeters. So just to here's the setup here. What I have up here is a tension protractor. It tells you both the tension and the angle of the force in the string. So
is that rod 120 centimeters?
Yeah, it's the longest one we have. I think it's 120 centimeters. And I backed it up with a shorter rod here just to make it a little bit more rigid. And I wanted to make sure that this was plumb so that my tension protractor up there would be giving me the actual angle. So that's measuring the angle from the horizontal. 0 is horizontal. And so it reads out this angle here. We're going to need that angle in our calculations down on the other end of this. Now, another feature of these little hangers is that they have an angle indicator built into it. So it's approximate, it's, every 5 degrees or something. But you can get a good estimate of what the angle is just by reading it off of here. So here I have a picture of just the meter stick and the forces that are acting on it. This is the force of the meter stick. This is the force of the hanger that's got the string on it. The string is pulling up that way, and the weight of the sign is over here. So as I said, so that you can follow along, this is 10 grams. No, I'm sorry. We don't know what that one is. We're going to find out what that one is. This one's 10 grams. This one is 200 grams plus the hanger, so it's 210 grams. I'm discounting the weight of the I love physics sign.
Have you taken your measurements yet? Can I make this vertical?
No, I haven't done anything.
Since we moved the table, this isn't vertical
It
anymore.
changed the, okay.
There we go. And that's what's nice about the double rod here, is it allows you
Well, also when you're setting this up, before it's all set up, you can hang a weight straight down on the tension protractor to make sure that it's reading 0 to begin with. And then you can put the string on. So everything is leveled pretty well. And this force reads what? 5 point. The red arrow indicates the force, 5.3 newtons.
And the angle looks like it's right at 55.
55?
So where the string crosses the angle here is where you read the angle.
So this is 55. Okay. So now we can set all the counterclockwise torques equal to the clockwise torques. And the counterclockwise torques, I'm trying to think again of which way you're seeing. Darn it. Yeah, that's the up one. That's this one. So taking the force in the tension in the string times the sine of theta, because we have to have really just the component of the force that's perpendicular to, so we're actually taking this perpendicular force acting out at that distance. I'm going to define all my distances from the pivot point. So I'm just going to call this R1. And R2 goes to this one right here. And R3 is this one. Now my pivot is actually right on the 2 centimeter mark. So we can put that in here. I hung this at the 98 centimeter mark. And the other one is at, I can't see with these glasses, 67. Nice thing about these meter sticks is you can read them from both sides, and they read the same on both sides. So 67 is the mark right here. So you can see that R1 is going to be 98 minus 2. The lever arm is from the pivot out to where it's being applied. So it's 96 centimeters. And R2 is going to be 67 minus 2, so it's 65. And R3 is from the 50 centimeter mark, which you can prove to yourself by balancing the meter stick beforehand on your fingers till you find where they meet, or just balancing it on a knife edge.
So can you hide mass up in one end?
You could trick, yeah. If you have students that think they know it all, then since this is hollow, you can stuff something down in it and actually change where the center of mass of this stick is. So you can check on whether they really are doing the math. So this is at 50 centimeters here for ours. Nothing's hidden. So this is, R is going to be 48 centimeters. So for this torque, I have the tension times the sine of the angle times R2. And then on the other side, balancing that, is the mass of the stick, which is unknown, times R3. And that's at a right angle, so the sine of 90 gives you 1. And then the mass of the hanger out here times R2 plus the mass of this hanging thing over here is M1G at R1. So you can solve this for the mass of the stick. Notice that the tension is in newtons. The tension protractor is calibrated to give you the force in newtons. Everything else we have is in grams, so you need to convert to kilograms and use, for these distances, as long as you use the same unit for all of them, you're okay. Technically, they should be in meters if you're trying to go for Newton meters for the torque, but the units will cancel out. So you could just use centimeters. And of course, G has to be in there. So if you calculate this out, and I'm going to magically calculate this. The mass of the stick comes out to be 150 grams. And voila, if you measure that, you will find that it is 150 grams. They're all approximately the same. You can find the approximate mass and the dimensions of this meter stick on the outside and the inside dimensions of the meter stick on the website. So you can make your own accessories for it. The other thing that is nice to do with students who are a little more advanced is to shorten this up and have this be at an angle like this, so you have like a crane. And so now you've got other angles involved, so you're going to have to measure what the angles are here. And it makes it a little bit more complicated. Now, back to this pivot. The pivot is designed to do regular meter stick torque. So normally you would have this slid through to, I can't get past there, slid through to the middle, normally you use it on the stick. And it's designed so that the center mass of the stick is below the pivot point so that it's a stable equilibrium when you're doing that experiment. But, get rid of this. It is also possible to turn this stick pivot the other direction So you can put it on a rod that's horizontal, vertical, do anything you want with it. And in this case, I've changed where it's attached so that it's attached in the center of the stick. So I can rotate it around like this. And so now I can do rotational inertia of this meter stick. I have mass in my pocket here.
As every physicist should.
Yes. You should see what's in my purse. I have a code node in my purse, always. And here I have, it's actually two, the axle goes through, so there's a place to put the meter stick, but there's also a place to put the pulley. And so you can use the pulley to apply the torque. And, all right, hold on. There. I've got it so that it'll hook. Thank you. Let me reach in here. I'm going to take some data, so let me reach in here and turn on this photo gate. This is, again, the wireless photo gate, smart gate. This pivot comes with this pulley so that you can use it in this fashion. And I've got to acquire that photo gate. There it is. Okay, so we're ready to go. And if you look at my screen now, I've got, are you seeing it? Okay. I've got the angular speed versus time. And I'm getting the angular speed from this pulley here. And so this is just a smart pulley. We used to call them smart pulleys, and we sold a separate product named that. But so this pulley is blocking photo gate number 1 on this. There's actually a dual photo gate here, but it's just using the one photo gate. And I can get the angular speed of this, which will be the angular speed of my apparatus. So let me just let it go here. Okay, I stopped it because I know it was going to hit the ground down there. You can see that this is a fairly straight line, and we can take the slope of it, and it comes out to be 1.65, which is the acceleration, the angular acceleration of this. Now, you can go ahead and use that to calculate what the rotational inertia is of a meter stick about its center. But rather than bore you with that calculation, I'm just going to do an off-axis thing here. I'm going to change where this is. I'm going to change this to 35. So now, instead of rotating about the center of the meter stick, I'm rotating about a point that is in a parallel axis, parallel 15 centimeters off. So the mass of the stick times r squared is the additional rotational inertia that you're going to get. And let's just try it out. Let it rip. Okay, I stopped it. So here you can see that the new pink line is at a lower angle because the acceleration is not going to be as much now. I used the same weight to accelerate it, but the inertia of the stick is much larger because it's off axis. So that's an easy thing to do. The other thing you can do easily with this is you can have it turned up like this. Let me just flip this around. Usually on these pulleys, well, it doesn't really matter actually. There are a complete set of rotational inertia stuff for our rotary motion sensor, where you can have a disc and a ring and point masses that are movable, and all of that fits right onto here without any additional equipment. So you can do the rotational inertia of all these objects as well. One more thing. As I said, the dimensions of this are on the website, and it is hollow. So the coolest thing is that you can also do a little electromagnetism with it. I have a dime here, and I'm going to drop the dime through here to show you how quickly it goes through. It's pretty quick. And then I've got a neodymium magnet, and I'm going to drop it through, and of course it's going to induce currents. It's falling. And you can see it took a lot longer to do that. And as the induced currents dissipate the energy of the magnet as it falls, then it's going to fall slower. Now, this magnet that I have just happens to fit down the tube, down the meter stick perfectly. That's because I own every type of neodymium magnet in the world. And I will point out to you that the magnets that we sell, the little ones, are quarter inch thick, and they're just a little bit too thick for this. So you're going to have to find your magnets elsewhere for doing this until I actually put one in there that we can sell that fits it. So that's it for the meter stick.
Wow, some really great stuff that Ann Hanks has just showed us with the meter stick. We looked at meter stick torque, and we were even able to pull in some of Lenz's law. And the really nice thing is, ladies and gentlemen, Ann Hanks does birthday parties too. So if you want this at your birthday party, she can bring her meter stick and do all of this great stuff. We want to thank those of you, again, watching nationally, internationally. Thank you, Samuel, for identifying yourself and bringing the northeast corner of South America into our Pasco little area here. So thank you, Samuel, from Guyana in the northeast corner of South America. Dan, just so you know, Samuel said that he absolutely loved the chain experiment. So somebody from South America is weighing in, so to speak, pardon the pun. Also, we have a greetings from Lynn, who is sending a greetings from the swamps and the bayous of Louisiana. Nice to have you with us, Lynn. And Douglas from New Mexico, representing the New Mexico state here across the United States. Lots of great people signing in, saying hello. Please continue with your questions. We're answering them feverishly. I see Janet is working desperately to get all of your questions answered, and we're looking for all of your shout-outs as you continue to join us. Really some great stuff from Ann Hanks, who showed us all the great things you could do with the meter stick. And then, just like we promised before Ann came out, we're going to demonstrate a supernova, and we're going to do it right here in our own little PASCO laboratory studio. And to do that, we bring back Dan Burns and his safety glasses, and all of us are now wearing our welder's helmets.
Yeah,
stand back, because we're going to be demonstrating a supernova. How are we going to do that, Dan?
Well, we're going to actually show two different ways.
Which ones are dangerous?
And so the first one is a common demonstration. The idea is a supernova is an explosion that happens in a very massive star toward the end of its life. And the structure of that star before it explodes is pretty interesting. It started out fusing hydrogen into helium, and then it collapsed a little when it started to run out of hydrogen in the core and got hot enough to fuse helium, and then it's making heavier and heavier elements, and it ends up almost like an onion, where the lighter elements are shells on the outside and heavier and heavier and heavier on the inside things like oxygen and silicon, and right in the middle is iron. That is the heaviest element that will fuse normally in a star. But when you try and fuse iron, you don't get energy out of it like the other lighter elements. It takes energy, and so it just starts collecting in the middle of the star like a big ball of ash. And it gets more and more and more iron, and at a very specific mass, the gravitational pull is so strong that the protons and electrons get pulled into each other and form neutrons.
Wow.
It's similar to a reaction that happens in some atoms called reverse beta decay. We know beta decay is a neutron changing into an electron and a proton. Reverse beta decay is an electron being captured by a proton in the nucleus, and you end up with a neutron. So this huge ball of iron about the size of a planet collapses into a ball of neutrons because they're neutral. They can get a lot closer, about the size of a small city.
Wow.
So essentially, in the middle of this massive star, you have a void. And so those shells start falling from all directions. Remember, the heavier stuff on the bottom, lighter stuff on the top, and they fall in and bounce out. And that energizes the supernova explosion.
That's explosion that we see. Wow.
There's also some neutrinos created in that also are a big part of the pressure that blows the star up. But it's essentially like this common demonstration. We have the heavier elements. Maybe this is silicon, and then maybe this is a helium or something, and the center of the supernova, the star, has just collapsed. And so this is falling like this. And also keep in mind, it's three-dimensional, so that's one problem with this demo. I'm just going to drop these two. And maybe we'll try it on the table here.
Sure, yeah, not to
Usually
do that
we
on
do
your
it on the
computer.
floor. We'll do both if we're able to find it. And so usually I ask my students when I do this, can a ball bounce higher than where you dropped it from? So if I drop it from here, can the racquetball end up higher than that? And it can. Now it's a little more impressive when you do it on the floor, since we already, so you got the idea. Now we'll see if I can, it's a little trickier too. And so
Up and out of the studio.
So that's one supernova explosion. And you can get the idea. What's happening is this guy comes and hits and actually starts to reverse direction. And so it's really, you're seeing a collision like this. Even though they fell together, this guy hits first, starts to change direction. So it's a collision like this. So it's not surprising this guy goes flying off and takes some of the energy from the ball. But wouldn't it be great if students could actually measure that? And so I was playing around with some smart carts and got that to happen. So I have the red smart cart with two masses on it. So this would be the heavier atom. And the blue smart cart, no masses on it, it's a lighter atom. And there are, forces in between them. Those are being modeled by these springs. And I have our heavy spring. These, you can buy these separately as an accessory for the smart cart. I have the heavy spring in front of the red cart and the wimpy spring in front of the blue cart. And if I drop them from, let's hear about here, I'll hold my finger here, see if the blue cart bounces higher. And it did, and it didn't even hit the end stop, which
pretty nice,
was my plan. Now, because these are smart carts, your students can measure the velocity of each cart and even do a calculation for the kinetic energy. So that's what I have showing on the screen here. The top is going to be the velocity of both carts, the blue and the red. And then at the bottom, I have the kinetic energy of each cart. I just called it energy, but it is the kinetic energy. And so we'll hit start. And so you can see I guess it changed my color scheme, but that's all right. But you can see in the velocity graph that the velocity after the collision of the blue cart is greater than it was when it came in. So here they are going down the ramp. They hit and come to a momentary stop. but the blue kart's going faster, over 1 meter per second, when it hit going about 0.8. Now, where did that come from? Sure looks like it got it from the red kart.
Sure,
if we
yeah,
go
you
down
can see
here
that
to the
decrease.
energy, you can see the, I did put these in before, oh well. So the red kart's energy is the blue line.
we got
And
them
you can
switched
see-
around, yes.
You can see it drops to very little here. And then the blue kart's energy is the red line, so it jumps up, it steals it from, that's just bugging the heck out of me. So in Capstone, you can change everything. And I had changed it before, and it didn't take, I guess. There we go.
Now
Isn't that better?
Yeah, absolutely.
Let's do it again,
Right.
but let them bounce back and forth, and it's kind of fun to watch that, too.
Okay.
I've gone to, boy, you're, pretty brave standing close to the supernova, JP.
Yeah, well, I've learned being around you, Dan. You've never risked your life before.
And then some fun stuff happens. But so students can analyze this, and you can fit in some astrophysics into your physics classroom, which a lot of kids really get excited about. I mean, what could be more exciting than a supernova?
Nothing is more exciting than a supernova in the classroom. And you're talking about like the energy and the particles being thrown off, and we're looking at I'm assuming we're looking at the neutrinos being thrown off here? Is that
so the energy that powers the explosion comes from two parts: the kinetic energy of the atoms falling in, and the heavy ones give up a lot of that to the lighter ones and send them flying off. Also, there are nuclear reactions occurring in that collision, and those produce neutrinos, which normally don't interact with matter at all, but there are so many of them that astrophysicists calculate that's a significant part of the pressure that's blowing up the stars.
Right, and I think that's what we try to capture when we're measuring and looking for supernovas,
Right.
right? We're looking for those neutrinos and that big flux of energy.
And those pieces flying out run into each other, and that can make heavier elements than iron. So a star only makes elements as heavy up to iron, but in that explosion, other heavier elements are made. Things like, well, I actually brought a piece of a supernova with me, although this might be a type 1 supernova. There's a piece of a supernova, gold.
Gold.
And so we would have no gold if stars didn't explode.
Wow, now there's an interesting fact for you. No gold if stars didn't explode. And that, ladies and gentlemen, comes from Mr. Dan Burns. Great demonstration, really a wonderful demonstration that just took place here. And of course, Dan Burns will also do birthday parties. So all you got to do is reach out, and Dan will bring his supernova to your birthday party. And really, we're learning a tremendous amount here. We need to clean the set. And in doing so, we're going to take you back to an interview with some of our great folks here at PASCO. Nolan, let's do an interview.
Thank you for joining us.
Of course.
Can you please introduce yourself?
My name is Janet Gomez.
What do you do here at PASCO?
I do social media. I also do our digital content. And I'm also a graphic designer.
Awesome. And what do you enjoy most about working at PASCO?
Working with Boomer, being able to just come up to people and take their photos, so they usually run away from me. That's pretty cool.
Right. How difficult is it working with Boomer?
You know, it's really easy to work with him. He's actually very cooperative. He could be a brat, though, but...
Is water wet?
No. Like, I had to think about that.
Who is the best NFL team, Raiders or the Cowboys?
Niners! No question.
What would you name your robot butler?
Alfred.
And what is your favorite element on the periodic table?
Iron.
Who makes the best tacos?
Chondos.
Yes. Who's your favorite boss?
You? I know I nailed that one.
All right, that'll show up on your review.
Thanks.
And we're back, and another great interview. We hope you enjoyed that as we kind of get to know the folks here at PASCO a little bit better. We've brought in John Hanks. You've seen him working with Ann before. They've been a team here at PASCO for many years, and we kind of threw out the question about, certainly I'm from Florida. We talk a lot about storms in Florida. We know the hurricane season is here. And one of the neat things, we just saw Dan talk about a supernova, but I was asking John if there was a way that we could actually demonstrate Coriolis effect, which really helps to explain a lot of what the storms do as they come rolling into our friends in and across Florida, taking a look at storms. But then John also got into, well, it's not just storms that you're looking at, it's actually taking a look at projectile motion and how the rotation of the Earth actually affects that as well. So it's taking Coriolis effect, a great thing that we all talk about, something that we're all very aware of, and now we're going to bring that big topic right here onto the table and take a look at the Coriolis effect, right?
Thank you.
Sure,
So,
absolutely.
yeah, down to size so that we can do some measurements. We're using the same plastic track that Jonathan showed you earlier, just a couple sections of it, and a printed part that puts the track at an angle on our rotating platform. So again, we have that on Thingiverse. So we've had a couple different versions of this adapter. This one is at a little higher angle because I found out that the faster the cart was moving, the bigger the effect. Coriolis effect, Coriolis force, is an inertial force that we introduce when we're talking about a rotating reference frame. If I look at this cart as it rolls down the hill, if the cart is being rotated by the platform, it's similar to an ice skater pulling in their arms, or we have a platform that you can sit on. So if the track is rotating with omega up as the cart comes down, that's just like pulling in your arms. What's going to happen to your rotational rate? Should speed up. What makes it speed up? Well, that gets tricky. You can talk about it in a lot of different ways. Some people just like to talk about conservation of angular momentum, and that works great for looking at the direction, how it's going to increase its speed. You can even calculate what the final speed is going to be. But it doesn't do a very good job of explaining what you would feel if you were on the cart as it's rotating around. If you are a molecule in the rotating storm system, or you're an astronaut up in a futuristic type of space station that is rotating. So some people call these fictitious forces. It is an inertial force. It is present in the rotating frame of reference, and that's what we're going to do today, analyze it from the viewpoint of the cart, not from the external viewpoint. The cart can measure a lot of things. It will measure its speed as it moves down the track. It will measure the rotational rate of the track itself with its gyro chip. And it has a built-in accelerometer, so it will measure directly that sideways Coriolis acceleration as it moves down.
Yep. Make it clear that it's sideways.
Okay, so the formula for Coriolis acceleration is a -2 times omega cross v. Omega is the rotational velocity of the track, and I will try and always remember to throw it in the same direction so that omega is up. V is down the track. So omega cross V is actually to my left, your right, but there's a negative in front of it. It's a negative 2 times omega cross V. So it actually creates a right turn, if you will. And you can actually demonstrate, it won't show very well here, so I won't do it, but you can demonstrate it for your students by starting it not in the groove. There's nice, deep wheels that fit into a good size V in the track that keep it from flying off. But if you purposely start it outside, you can see when you rotate it one way, now, there we go, as it comes down, it actually stays right against this rail. But if you start it on the other side as it comes down, it actually derails and goes flying off, which is a nice demonstration in its own. So you can prove which way the force is. What Ann's talking about is that we're measuring this acceleration directly. There is several different ways to measure by an encoder as it comes down. The acceleration is an acceleration chip that's on board that has a direction as well. And there's a gyro chip that's actually measuring the rotation of the track. So we can do all of this at once. We'll take live data and then just look at that graph. The only other thing that I wanted to talk about was in terms of relating to things on the surface of the Earth. If you look at air movement, it's more complicated because the Earth is round. And so say, well, let's do a projectile, a long-range projectile. At the equator, you think it's moving really fast, but its radius, the distance from the rotation axis of the Earth is not changing. Where if it's up more closer to the North Pole, then that velocity along the surface of the Earth is much bigger. This is a simpler problem because we're going down a track, but the speed is still changing. Omega is still changing. All these variables are changing as it moves down, but since we're measuring it real time, we can calculate it. Should we just go ahead and take the data?
So this is a graph of?
This is a graph of, well, 2 things. On the graph will be both the measured acceleration from the chip and the
measured acceleration perpendicular to the track?
Yes. Z on our equation here. Right angle to the velocity. And the calculated centripetal acceleration, which includes 2 measurements, the velocity down the track and the angular speed. Want to go ahead and just do it? Let me get started. Okay, you got it started. Okay, wait for it.
He has a start condition.
Wait for it. There we go. And a stop condition too. So once it's gone a certain distance, it stops. The acceleration data itself is a little jagged. It is real acceleration data as this is coming down, especially when it goes at the transition between the two. That causes a little bit of a vibration. And it's changing the colors so they show up a little bit. The acceleration, why don't you click on the acceleration there and do a little smoothing, show them what that looks like, and then back off. So if you want, you can smooth a little bit. I actually like the noisy data. It's real. That's what the acceleration data actually looks like. The other things that you need to do more carefully that we didn't take the time to do is you can zero the gyro. So when you start this off, make sure it's not rotating, and zero the gyro chip because it can be off a little bit. And also even the acceleration is being measured. You can start by having it be zero as well. But what you can see is the 2 data track very well. Now, one isn't pure theory. Even the centripetal acceleration calculation is still using real data. So what's, to me, the most amazing thing about this is that we're measuring all 3 quantities at once. We're measuring the actual speed of the cart, the rotational speed of the track, and that sideways acceleration. The speed's changing, the angular speed's changing, and the acceleration changing all at once. Did I say centripetal? Yeah. So when you do the transformation from normal inertial, non-accelerating reference frame to a rotating, that's you introduce both the centripetal and the Coriolis. I mentioned that there's other versions of this adapter that we make. The flat one is perfect for just having this spin around in a circle and measuring the centripetal acceleration. Said it right that time. But yeah, here we're measuring Coriolis.
And those adapters are 3D printable, right?
Yes. And if you didn't have a 3D printer, and you really, really wanted one, I'd probably even send you one if you wanted one. So, anything else? All right.
Very nicely done. Ladies and gentlemen, Coriolis effect with John Hanks and Ann Hanks. Another force of physics that you probably don't realize is the force that holds people together. John and Ann now married over 45 years, so congratulations to them. You really got to wonder what their dinner time conversations are like. I think you just got a sample of that today.
I don't think they wonder. I think they know very well
they
probably
probably
what
know.
they're like.
Yeah, yeah. Yes, as they correct each other on, did you say centripetal or did you say Coriolis? Got to be interesting conversations. We are wheeling in our next set, and you just saw John Hanks use the Smart Cart, and the Smart Cart is a really phenomenal device in its ability. Many of you have it. If you don't have it, you certainly want to get it, as it measures acceleration, velocity, and force. But we've actually taken the Smart Cart and we've taken it a step further. We've built in the opportunity now for you to use a device that makes the Smart Cart motorized. And with that, you can do a whole bunch of experiments, all of which are measurable, all of the great things with the Smart Cart, now enhanced with the motor. And the really neat thing about the motor, I think Dan was showing the Blockley coding before, it can all be coded so that you can now program this device to carry out your wishes as you start measuring some interesting things in physics. So what are we going to measure now, Dan? You've got a very interesting setup.
So we have
what are you going to do here?
We have a lot of things going on here. I have a Smart Cart, and I have our rod stand adapter that allows you to mount different sensors to the Smart Cart. And I've mounted 2 of our wireless motion sensors. This is definitely something that was difficult, if not impossible to do with the old wired ones. And I have one pointing at this background and another one pointing at this one. And the Smart Cart motor is going to make this easier. It's going to drive the Smart Cart down the track at a fairly constant speed, and the motion sensors are going to measure the velocity of the cart relative to, well, let's call this the x-axis and this the y-axis. So they're going to measure the components of the velocity. And so this is in our experiment library. It is a lab written for the Smart Cart motor.
What's it called?
Students, components of velocity.
Components of velocity, wow, all right.
And students, just search Smart Cart motor and you'll get all the labs associated with it. I think it was probably one of the funner things I've done here at PASCO is writing the labs for the Smart Cart motor. And so it will, students can discover the relationship between those 2 velocities for themselves rather than just being told. And so this usually is even for students that have had trig, it's usually a tough idea early in their physics class. They're like, hey, learn sines and cosines. Now you're telling me I have to do something with them?
Right, here's a great application of it as we break them into the 2 different components.
Right. So now you don't really, the lab that's written doesn't have both of them. They can measure the X and the Y separately and do the lab, but you know, go big or go home, right? We've got plenty of motion sensors here. So we put both of them on there. And I've also found if you tip the track down a little bit so that gravity cancels out friction and air resistance, you don't really need the motor, but let's not tell our customers that.
Right, yes, you need
the motor. Makes it easier. Right. It definitely does. There's so many other things you can do with the motor. You're going to want one. So I have a, oh, is it doing that again? So I have a capstone display.
Possibly.
And I have the top screen is the velocity of the cart. The bottom screen will show the X and the Y components. No one's saying, let's try this again. That didn't seem to do anything. I'll see. And so the bottom screen is going to show the X and Y components. And the thing that's a little tricky is the motion sensor that's pointing at the x-axis is measuring the motion of the cart relative to the y and vice versa. And so that's actually a good reason to do them separately. And so I have the track at about a 20-degree angle to the x-axis. So we should expect the y component to be greater than, or the x component to be greater than the y component. Let's see, I think I might have switched them when I hooked them up. Oops, I hit it twice. I have a stop condition in there, and I keep forgetting that. So I hit stop, and it's really starting again. Let's do that again. And let's... So these backgrounds aren't working as well as walls. I had it working better than that a little bit ago. But I also put the magnitude, taking the x and y components, squaring them, adding them, taking the square root, and graphing that at the top as well. Oh, it's going wacky on us again. I saw it for a little bit, though. So that's not a problem with our software. That's my output to the HDMI cable for some reason. There we go. Let's do that one more time. See if I can get a little better data. But that one is rock solid. They're usually both like that, but still not too bad. So students can take those x and y components and look at the relationships between them and the velocity of the smart cart. They can do their own calculations. For measuring the angle, I found you could just print out a protractor on a piece of paper, and real large. That makes it real easy, but it's not a protractor then. It's just an amateur tractor. So somebody laughed. So this probably took me more to set up than anything else, JP, but I'm done already.
Wow, that's a very quick demonstration. But Dan, you're not really done, because I want to ask you, you said that you enjoyed writing some of the labs for that smart cart motor. What else is available? What great things did you put in the library for our folks at
Another
home?
one with the motion sensors, you can measure the velocity of the cart relative to another cart. So that one's pretty good. You can very precisely drag a friction block and see does the force of friction depend on the speed of the block. Mm-hmm. And students are usually taught, no, it doesn't matter. And in this case, they can find out for themselves. Is the textbook oversimplifying? I won't give away the answer. That's a student investigation.
Great.
And so there's like 6 on there.
Awesome. Well, these are all available. Dan has written some great labs. He writes a tremendous number of labs in our physics library. PASCO.com. Just take a look at our libraries. You'll find our our activities library, as well as our video library, where Dan explains a lot of these complicated concepts and many of the videos that you'll find there. So check it out and take a look. And thank you, Dan Burns, for breaking things up and resolving components. We just got a very exciting hello from Wakanda, so we want to say thank you, Black Panther, for joining us today from Wakanda. And I think what we really need are some good vibrations. And so, not to bring in the Beach Boys, but what we will do is bring in Brett Sackett, who's going to be looking at some good vibrations. Let's move this set, and let's bring in Brett Sackett.
Howdy, JP.
Hey, Brett. Nice to have you here. Thank you for bringing some great vibrations for us.
That's right. We're going to get some things plugged in.
We have already been seeing so many neat things that we've been using the smart cart. We've been looking at energy. But what you're going to do is a little bit different. You're going to be bringing in some very complicated concepts, but you're going to be doing it with just string and vibration, yeah?
Yeah. All right. Oh, a microphone.
And
yes.
Right. Let's not have any more of those troubles. And we dressed to match today, Brett, which is nice.
Absolutely. Although I forgot to put my bow tie on.
Oh.
I was ready with it.
People may not even recognize you without it.
Yeah, I get that. All right. So
let's see. So we're going to be looking at standing waves on a string. So let me talk about some things I have going on here. I know there's a lot of cables and wires going around. So I have the PASCO string vibrator, and this right here is the sine wave generator, so we can change the driving frequency of the string vibrator. And so I'm going to just connect this up here with some banana cables, and we'll make some final measurements. Of course, we always measure with an aluminum meter stick now, because that's what we do. So that just needs to be a little bit higher. All right. Good, good, good. All right. And then all this stuff happening over here, I have strobe modules, which is going to get very interesting on the camera, I bet, because they're facing that way. And so what we can do is we can strobe the string as a standing wave is happening, and we can see what that looks like, and basically freeze that wave in space, which is really cool. So let me talk about that. We've got an elastic cord over a pulley with a mass hanging from it. That's about 500 grams. And so let's say we remove that mass first. And so I just have this elastic cord here. Now you'll see it stretches, and the great thing about this cable here, this cord, is it's great for demos. It's really easy to see in a classroom environment, so it works great for demonstrations. So if I turn this up about there, and if you can see, I'm driving at about 40 hertz, and you can see this string, just as it's hanging there, is already starting to wiggle around. But what you want to do as a demo with your students is just as you're introducing them to the concept, just pinch part of the string at the end, and that's going to be your fixed endpoint or your boundary, and then just apply a little tension, and you'll see you can set up standing waves just by applying the correct amount of tension. So you have a length, you have a fixed amount of tension, and you can find standing waves where you have a series of nodes and antinodes. And so as you pull it and change, when you hear that bouncing, that means it's reaching resonance. So you can turn down the amplitude on the sine wave generator to quiet that down, right? And so you can see there, I got my boundary on each end, and I've got two nodes in between. If I pull it a little bit more, can I find another one? Not really. Once tension's going to be a little bit too high. Now, what I'm doing here is actually pretty complicated because I'm changing the tension and the length at the same time, and that's typically not how you're going to do a lab. But just as a demonstration for your students, showing them that the things that affect the standing wave or the resonance modes is length and tension. So you can start with that. Then we want to fix some of the parameters. And the first parameter we're going to fix is we're going to have a fixed tension and a fixed length. So then we can investigate, well, what are the frequencies that will cause standing waves? And the fundamental, where we get half a wavelength here, which would be n equals 1, we'll try and find that by tuning the sine wave generator and find what frequency gives us that first fundamental. So if I turn this up right now to where I had it, you can see it's way too high of a frequency. So we'll go down and see if we can find that first fundamental. And so the fundamental is going to be half a wavelength. So we can kind of play around. And what you're really looking for when you do this is you have a boundary there, and this right here at the end of the string vibrator, you want this to be a node right there as best you can. Of course, it's going to be oscillating, but what you'll notice is that as you change the frequency, you can actually move the node out onto the string. And that's not what you want, because we want to know, because we want to measure, we want to be able to measure that length from end to end, right? So somewhere around there. And then we will, on the sine wave generator, I'm able to store that frequency. Now that's stored, and now I can increment up. And just with one hit of a button, it's going to take that frequency and double it. And now you can see, have a node here, 2 antinodes, and I can keep doubling that frequency. I can adjust the amplitude as I go up, and you can see I can just keep finding these modes just by changing the frequency and just kind of, and when it gets high enough, you'll start hear it once it gets into the audible range. Now it's, as it gets higher in frequency, the amplitude keeps getting lower and lower, right? So maybe we can, if we can maybe dim the lights a bit. Woo! And then, so that's 30 hertz right there. How's that?
That's annoying. You wouldn't do that to your class.
Yeah.
You do it to the camera.
Yeah. Maybe if I turn these around, does that help?
Are you at 30?
No, I'm saying, is that like freaking the camera out? Okay. There we go. All right, so now what I've done is I've taken the strobe and I've taken the frequency slightly out of phase so you can just watch that wave evolve through time. And if I freeze it, then you'll see it stop once I match the frequencies up. Right, so there I've frozen that at what looks to be the maximum there. The other control here is I can change the intensity. And so that was and let me know if the camera's picking that up or not. That's good? Okay. So you can adjust the frequency and the brightness. And so what happens when you adjust that brightness, it's changing the pulse width of these LEDs that are flashing. And so if I take this slightly out of phase and you see it moving around, because I've taken the intensity down, I get a much finer detail on the string, right? Yeah, because it's not pulsing for as long. If I increase the brightness, you're going to see it's going to make the string blur a little bit just because it's pulsing for longer. All right, that's cool. And then let's increase this frequency again. So now I'm at 45, and I'll change this to 45.
You can actually make it straight.
Yeah, you can freeze it when it's.
That's exciting.
Yeah. There we go. So now we're up to 60. Here, I'll take it 1 hertz out of phase so you can see it kind of wiggling there a bit. Right? So that's cool. There's another thing we can do. I'm going to drop the frequency back down. Oops, that was actually going the other way. I'm in the darkness. I can't really totally see what I got going on here.
Well, that's actually a pretty neat effect.
Yeah, so now it's pulsing. It's strobing, at twice the frequency. So we're getting like a doubling effect there. There we go. How's that? Well, that's awesome. The strobe has another feature, which is you can connect a PASCO photo gate up to it, and instead of the strobe just going automatically, what I'll do is I'll change the mode to trigger, and it's going to trigger off this photo gate. So if I come in, what's that? Oh, I got to turn it on. There we go. Yeah. So now, every time it's blocked, it gives a flash like that. And so then we'll just come up here. And so now you see, as I move this photo gate through this standing wave, what it's doing is it's freezing that wave in space for the position that I've blocked it.
But it looks like you're dragging the string with
Yeah,
the photo gate.
right. Now, okay, so everything I'm doing here is great for demonstrations, and the elastic string, like I mentioned earlier, great for demonstration. It's not the greatest string if you're going to do the lab, and that's because the string doesn't have a consistent linear density as you stretch it out. As you stretch it, you're changing the linear density, and that's going to make your calculations all weird. So what we do when you can do it, plot it for different tensions and stuff like that, but what we're going to do, there's definitely an order of operations here. You want to remove the mass first. Right? Okay. So now we're going to remove this string vibrator. I have a second vibrator with a different kind of string, one of our favorite strings, which we call it physics string. Because it is so good for doing physics labs. If you caught me and JJ some time ago, we actually showed you the PASCO massless physics string. All right, so this string, yeah, it sold out immediately. This string has a different linear density, and so you'll find that calculations with this are much better. They work very well. And so the other thing I'm doing as I'm lining this up is just straightening things out so we get nice, super awesome vibrations. Good vibrations, right, JP?
Good vibrations.
That's right. And then we will power this up using the string vibrator like that. I've already done the calculations, so I know that the fundamental should be around here. Yeah. All right. Yep. So somewhere around there. Does this show that string? I know this is a very small string. Is the camera, can you even see that? Maybe that helps a little bit. Yeah, so this is a very low density string. Oh, look at that. Oh! Of course, we can strobe it too. And then I can, again, step through the modes. Oh, yeah. Woo. So things, so we are, because we're keeping the length fixed and we're finding frequencies, as you're explaining this, how all this works to students, varying the, how can we increase the frequency? So the wave speed is a function of the square root of the tension over the linear density, so we could increase the frequency by increasing the tension. And if you play a musical stringed instrument, then as you tighten the string, the frequency goes up. You can change the length, and again, if you play an instrument, as you decrease the length that the string can vibrate, the frequency goes up. That's why, guitar players, when they're jamming, they're like this, because they're really shortening the vibrating length of the string to get those really high notes. So, and so with this string, we can actually get, you can actually hear it do some pretty high frequencies here. The amplitude is so small at this point, it's within the width of the string. But you can really hear those modes. There we go. Yeah. All kinds of cool stuff. So that, in summary, is the string vibrator with the sine wave generator and the strobe system that allows you to do some really good demos in your classroom.
And the really nice thing, Brett, is that this is actually very low tech for some really high-level concepts, isn't it?
Yes, it was really nice not having to use like a computer on this demo.
Right, yeah, we didn't have to. We didn't really have
simple.
to collect data. We were actually able just to watch it.
Yes.
And get the concept across. Very nice
Absolutely.
demonstration. Ladies and gentlemen, Mr. Brett Sackett, and some good vibrations. Now, the really neat thing about what Brett just did, you saw the waves, but towards the end there, you actually got to hear the waves. But we want to take that a step further. You heard the waves, now we want to control those waves. We want to actually harness them and force them into a tube and torture them in such a way that we can demonstrate a new concept. And who better for torturing than our own J.J. Plank, who is bringing in a resonance column, who's going to be doing some things with those same waves, the waves that you were listening to, the different types of resonance that you were listening to. And now J.J. is going to do some really neat things as he pushes them through the tube. Remember, we are live. Every time somebody leaves the set here, they go back to the computer banks where they're answering all of your questions. And so keep those questions coming in. Keep your shout-outs coming in. I think we've only got one more demonstration after this one, don't we? Yeah, Ann Hanks will be closing us off as the pitch hitter, and we'll be bringing Ann in to close us off. So if you've got your questions, let's get them in. You've got your hellos, let's get them in. You want some more torture? This has actually been recorded, so you can watch it over and over and over and over again. JJ, what are you going to do for us? What's happening here now?
Let me put the magic mic on.
Yeah, our folks want to hear you. Perfect.
There we go. So, JP.
JJ.
What we're going to do is some activities. Some can be considered a demonstration, but these are actually quantifiable. Students can do these as a lab activity. We have some write-ups to support that, but we are going to be doing standing waves in an air column.
Ah, okay, because we just saw standing waves.
That's correct.
Brett was just demonstrating them, and now we're going to be using that same concept, looking at standing waves, but you're going to be using it within this nice column here, correct?
That is correct.
I can't wait to see it.
All right. So, let me just check with Nolan. Is my screen okay? Perfect. So, this is PASCO's resonance air column, and it may not seem like much. It's a plastic tube, right, that's got these convenient stands on it to keep it elevated off the table. And then there's a slidable plunger in here. But what I've discovered is, after trying to do these activities and these demonstrations with other setups, giant tubes, I remember at one point I was using the old tube that the tracks would ship in, right? They work well. This works amazing, and it works amazing for audible frequencies that we would have in our classroom, not so much, those really low frequencies or really high frequencies, although it can do that. It's an amazing tool for exploring how sound waves behave in an air column. And in this case, with the plunger in place, this is a open-closed air column. One end is open, one end is closed. But we could remove the plunger entirely, and this could be an open air column. And I mean, I've got pieces of PVC that can help me do open as well. And I'll show you at the end of this just something neat that I was shown some time ago that just absolutely, I had never seen it before. It's something so simple, and so I'll explain in just a second. But what we're going to do with our students is we're going to give them tuning forks, right? And so these tuning forks will produce sound waves. And they produce a sound wave at a fixed frequency, which is written on here. This one says 320. Let's see if we can go a little bit higher. Here's 341. And so sound waves are going to be generated. And if you hold this tuning fork near the open end of this pipe, those sound waves are driven down the pipe. And now what we want our students to sort of discover is that at the right length of pipe, this system starts making a louder sound. You start hearing a louder sound, and then we'll call that resonance. It starts to resonate. And what's actually happening is those sound waves are being reflected back, and when the speed and frequency and length are just right, you get standing waves established in the pipe. It's just like we saw on the string. And when those standing waves are, or when those standing waves are established, this system starts to make, the whole thing starts to make sound louder than you would hear with just this tuning fork. In fact, if I strike this tuning fork, you probably can't hear it. I mean, tell me if I'm correct, Nolan, if I hold it a little closer, you can hear it there, right? But out here, we can't hear this. And in fact, when I hold it over the tube, we can't hear anything either, right? Because I remember I said the resonance is a combination of lots of things, including pipe length. And so Dan is going to help me. So I'm going to strike that tuning fork, and as he draws the plunger out, keep going. Right there. And so I'm going to do that again. I'm going to strike this tuning fork, and then Dan, you can go back and forth at that location. And you can hear the sound. Now you can hear the sound. We can hear the sound in the room, right? And teachers love this when every group is going at the same time, right? And so what we've done is we've found a length of pipe where a standing wave is established. And now this, like I said at the beginning, the system is open-closed, right? And so there are boundary conditions that those waves have to meet. And one of them is that standing wave at the closed end of the pipe, what we have here is a node, right? And at the open end, we have an antinode. And if we had had open, we would have had an antinode and an antinode at this end, right? Now that's a pretty general condition, right? Because we didn't talk about anything in between the antinodes or anything in between that node and antinode. So what happens if we draw this plunger out even further? Goes quiet, still quiet, and then keep going. Keep going. Right there. We find another location where all of a sudden this tube, this just air column, starts making more noise. So what's going on here? Well, this tube setup where it was closed and open, the standing wave that gets generated in there has to have a node and an antinode, and so that can happen when there's only 1/4 of a wavelength in there. But we just found another location where it happened again. So what's going on? You have to have a node and an antinode. So does that mean we've added a whole nother half of a wavelength? Because in between there, we wouldn't meet that condition again. So we must have. So here, this sound wave that's in there has to be experiencing a standing wave where there is a node, antinode, and there has to be now a half a wavelength in between, a new half wavelength. Right? And if we know how fast sound waves travel, right, and we know the frequency that we're generating, we can calculate what the wavelength is, right? And so we can compare the calculated wavelength to what we have just experimentally determined. So this is not quite one wavelength, but it's 1/4 plus a half a wavelength. So there's 3/4 of a wavelength in here, right? And we could keep going. And obviously, eventually, we're going to run out of room, right? But we can do different frequencies. So this is 512 hertz. And so, keep going, right there. And so clearly we could tell using our ears, this is where we're resonating, right? Look how much shorter that distance is than the first one. And so if we keep going, right there. And so we had the same thing happen. Now we've got 3/4 of a wavelength, but look how much shorter the length of tube is. And as Dan popped off, there are clips that come with this system, and they snap right on the tube to help you mark where different things are happening, right? And so we can take these clips, and so with the plunger in this position, we had resonance. We can snap a little clip on there, And students can take their meter stick and they can measure the length from the end of the pipe to the plunger, 49 centimeters. And we know 49 centimeters is equal to 3/4 of one wavelength. And we could keep going, right? Because this is about what we added, that half wavelength, we could add another half of a wavelength and keep going and still meet those boundary conditions. Now, tuning forks are nice. They're very convenient, found in nearly every physics classroom on the planet, right? But I'm constantly hammering this and trying to find it. It can be difficult sometimes. Also, I want to point out, a standard tuning fork like this, if you strike it hard enough or on a hard surface, you will get overtones. You will get frequencies that are not the one that you care about. What I've found is, for tuning forks like this one, if you grab it instead of by the handle here, but just at the base of the forks, the tines, and you strike it right in the middle, you can avoid those higher frequencies. Just a tip. So what we can do instead is, PASCO has this little mini speaker that's designed to fit right there on the end of the tube. And this can be driven by any function generator. This one is just PASCO's digital function generator, right? And we can generate constant pure tones using a sine wave, which is exactly what this does. So it's at 1,000 right now. This was 512 hertz. So what do we suspect the length of pipe will be at the very first? Probably shorter, right? So let me turn this up. Right there. See, it's much louder. Now draw it back just a little bit. Much quieter, right? You can barely hear it. And so right there, look at the length of pipe is much shorter. In fact, it's about half as short as the 512 hertz tuning fork. And as Dan keeps drawing it back, he finds more and more. Because remember, every time we add half a wavelength, we're going to be at resonance again. We're going to meet those boundary conditions. We can even play music with it. And so we've been using our ears, let me turn this down, we've been using our ears to sort of determine where to stop drawing the plunger out. We could take that a step further. I'm going to go over here. And we can use something like a sound sensor. So this is PASCO's wireless sound sensor, right? And let me get my computer up. And so we can use the wireless sound sensor to measure sound level data. We can actually quantify how loud it is, right? It gets louder when it's resonating. This is the tool that we can use to help us figure that out. And now it's mounted to the smart cart, which I'll explain more about in just a second. So stay tuned for that. And so I'm going to open a file that I have saved on here called air column. And in this file, I've got to connect my sensors real fast. So I should probably turn them on. So sound, smart cart, I'll just connect that now. We're not going to use it. And so I've got a graph of sound level versus time. So I'm actually going to move this back just a little bit. So I'm going to turn this on. Actually, I'm going to reduce it back down to probably about 340. So I'm going to turn the frequency down to 340. There's 348. All right. I'll move that a little bit closer. Yeah, and so now what I'm going to do is I'm going to click record, and we're going to do this while I'm talking because it's going to pick up my voice, but we see the sound level, and Dan's going to move the plunger, and I'm going to watch this graph, and I'm going to tell him right where to stop because it's going to be the loudest, the point where the graph is the highest. Okay, ready? Go ahead. Oop, go back. Right there. Turn that off. And you can see I stopped him right in my graph area here where we were at about 65 dB. right? Everything else was sitting at about maybe about 62, 63 dB. So when the sound level is the greatest, that's where we stop. So students can actually, you know, be much more technical in terms of this application, really fine-tune where those, where the plunger should stop so we can get resonance. And so that's, you know, the main application, but I just wanted to show everybody one other thing too, one other neat thing that I've been sort of playing around with. I'm going to move the speaker a little bit closer. And so the reason I have the sound sensor attached to the smart cart is because, Dan, do you mind grabbing that track for me, please? I can take this smart cart and actually measure the sound level. And so in a sound wave, in a standing sound wave, we get areas of compression and rarefaction, right? Where areas are higher pressure compared to others. And they're, you know, it's vibrating. And so we can actually get physical movement of this tube, right? Where the sound is technically higher above the tube. Now, we may have seen a Rubens tube, right, where it's got holes in the top of it and little flames, and the areas of higher pressure will push gas. Let's say you've got propane in it, will push the gas out higher and you'll get taller flames. This is kind of like that, but with the sound sensor instead. So you don't have to have burning stuff in your classroom, even though burning stuff can be fun.
Disclaimer, we don't burn stuff in our classroom.
We don't burn stuff. So let me get rid of that. And Dan, do you mind drawing that plunger out for me? Till the face of it, keep going, right there. Well, forward a little bit, right? So this flush with that marker. There, perfect. And so I have this marked ahead of time, and I'm going to turn my frequency generator back on since I just turned it off, up to 2400 hertz, which is really noisy. Not a friendly sound. But what I'm going to do is this length of tube corresponds to a length at which we get standing waves established in there. And like I said, I figured this out ahead of time, but we get several areas of nodes and antinodes. And what I'm going to do is measure the sound level while simultaneously moving the sensor along the length of the tube. And in my graph, I'll plot sound level versus position. My smart cart, I accidentally turned it off too. Me and my fumble fingers. Let me just turn that back on. And so we can get a graph of sound level versus position. And so we can tell where the areas where the antinodes are in the tube, how far apart the antinodes and nodes are, right? And so it's got to be quiet when we do this. There's a bit of a fan above me. We'll try it. We'll see what happens. But I'm going to click start. Actually, I'm going to turn this on first. We'll get some sound going, establish the standing waves, and then I'll record data as I move that cart. So here we go. And there you go. And so on my graph, you can see very clearly there in about the first half of the graph, the left-hand half of the graph, there are three very distinct bumps in the graph. And those represent antinodes along this tube. And it was right about in this section. Now I got a little flat in the later sections, right? And that just could be you know, spatial constraints of the tube. I didn't spend a whole lot of time setting it up very accurately. But what we could do is we could take our tools inside our software now, and we can figure out exactly how long one wavelength is, right? And so in a standing wave, one wavelength, you're going to see 2 antinodes, right, and 3 nodes. And so this is telling me that we've got a wavelength of about, bless you,
Thank you.
We've got a wavelength of about 16 centimeters. And so if I do the math, 2400 hertz, 344 meters per second, we know the speed of sound, we know the frequency, we can figure out, we can calculate what the wavelength is, and it's about 15 centimeters. So we're very close. And we could have redone this and tested it in different areas as well. So
you're so excited about these waves.
Yes.
I mean, you're really so very excited about these waves. But this is again, one of those things, you kind of started with waves, we're back in waves. This is one of those things that we teach every year, we teach at every level, and yet we always struggle trying to show these things, and now you're showing them very easily.
Yeah.
Really, with some very nice stuff. Are these labs available if folks wanted to look this stuff up?
Yeah.
What can they find?
So the labs with the resonance air column, we have both advanced physics applications for it. So if you go to our AP physics manual, advanced physics 2 manual, sound is in there. We also have on the resonance air column webpage, the product webpage on PASCO.com, there's all kinds of activities in there as well, including ones with the frequency generator and with tuning forks.
Oh, that's awesome.
Yeah.
So you saw it here, but you can do it there. All you got to do is go to PASCO.com, download some of our labs. Are there any videos of this?
There is now.
That's right, because this has been recorded. So we will have these videos for you. You'll have access to this. You can watch all of this and all the labs that JJ's put together. So ladies and gentlemen, Mr. JJ Plank.
Thank you very much.
Now, as we push this out of the way, I just want you to know you have now had 16 great demonstrations, and we're approaching the 17th. And the 17th demonstration is bringing together some of the equipment that you've seen already and bringing in some new equipment that many of you have, or if you don't have, you're definitely going to want to have, because what a neat concept is about to be demonstrated here. You've probably heard about the Helmholtz coils. You may not have used them, but now you're going to get to see them in a way that you might not have seen them before. We're bringing in the smart cart. We're bringing in our magnetic field sensor. We have our Helmholtz coils. We have our physics expert, Ann Hanks, who's going to bring all of this together and do a phenomenal demonstration for you. Our last demonstration. So remember, we're live currently, so if you've got questions, get them in. We just let JJ go, so he's now answering those questions for you at the computer bank. So any of the questions you have, get them in. Any of your shout-outs, get them in. We are ready now to take a look at our Helmholtz coils with Ann Hanks. Ann, what are we going to do?
Well, of course we're going to use the smart cart to do
Something phenomenal, right?
Yes,
Yeah, like the smart cart's been a theme today. We've seen it a lot.
You know, it's great. You can even measure magnetism with it.
And I think that's great. You put that sensor on there, and we're going to see that. Go ahead, Ann. It's all yours.
I'm just got to connect up to my sensors here. There we go. All connected. Okay. So just to explain, I'm going to do the magnetic field first. It's right here. There we go. So Helmholtz coils are two coils with the same number of turns on them. These have 500 turns on them, each coil. And they're a particular distance apart. If you take the diameter of this from center of the coil to center of the coil, it's 21 centimeters. So the radius is 10.5. And these coils, in order for it to be good Helmholtz coils, have to be at 10.5, the same as the radius of the coil. The separation of the coils are 10.5 centimeters. So we're going to look, the reason you use Helmholtz coils is to make a uniform magnetic field in the center here. So you can do experiments in here. That's for next time. But today we're just going to measure that field all the way along the center axis of this. And what I've got is a smart cart with a wireless magnetic field sensor on it. It's just sitting on it. So it happens to come out to be just the right height so that I'm going down the center of the coil with the track in this position. So I can keep track of my magnetic field with this magnetic field sensor, and I keep track of the position of the cart to know where that magnetic field sensor is. Now, in order to make it be in, 0 in the middle here for 0 position so that my coils are centered around a reference frame of 0 here, I'm going to line up the end of the magnetic field sensor with the center of the coils the best I can, right where the sensor is.
Say when.
Yeah, that's the best I can do.
Okay, it should be 0.
So that should be 0. Now, that's the nice thing about it is that in the software, you can tell the software, I don't want it to 0 again, the smart cart to 0 again when you start recording. I haven't started recording yet, but it already knows where we set the 0. So we're going to leave that 0 on, and then I'm just going to roll the cart through and plot the magnetic field versus position. Oh, wow. Guess what? There's a magnet in the end of my, I should.
You turn the current on.
Well, that's perfect. It shows there's no field because I didn't actually put any current through the coils. Thank you. Okay.
Did you move your
No,
sensor?
I'm good. You want to
start it this time?
hit record for me?
Okay. So
This time I'm going to turn the current on, and I'm putting about 1/2 amp through it.
Okay, it's running. Go ahead. So getting something this time?
Yeah.
There.
Yeah. So I should have stopped it before it got to the end here, but and I didn't quite have it centered right because my curve is not the curve is not centered on 0, but that's okay. It's close enough. So the coils are actually positioned about here and here, and the addition of the 2 fields makes it be quite uniform. So as the field drops off from this coil, the other field is increasing from this coil. So the 2 add up to be just a constant value through the center. So this flat top is where the center area of the coils are. Now, the equation for Helmholtz coils is, as a function of the x position through here, is given in this complicated equation right here, which I have put into the calculator in Capstone. So I'm going to add that calculation here to this. Come on. Here's the theoretical curve. And let me change the color here. I'll make it red. So there you see the theoretical curve and is in red, and the actual curve is in blue, and they match really well. And I didn't compensate for anything here. This is actual measurements. If I had zeroed correctly, they would have been lined right up on each other. So let's go on just one step further. I'm going to take this and move the coil so that it's the wrong separation. Instead of being at 10.5, I'm going to put it at about 20 centimeters. There's actually a set screw down there that I could loosen to do this better. Help. I can't reach it. You sure?
I think so.
How far?
Well, keep going. That's good enough. So let me just put this back so that the coils are centered on the approximately the same place they were before. And now, current's still on. Let's record this one. So there you see that the coils are too far apart, so that when the magnetic field from this coil is dropping off, the magnetic field from this coil hasn't picked up enough to compensate, so it doesn't fill that in and make it constant in the middle. I also have the formula, which is for any distance that you like to have the coils apart. The distance d is the separation of the coils, and I can add that in here. I think I had it in the calculator for 20 centimeters, but let me see. Yeah, there's the 20 centimeters. We're not quite 20 centimeters apart here. We're only at 16. Let me change the calculation to 16. There. Oh, see, it matches it very well. So we've shown you today a lot of ways to use smart carts for things that they never were intended to be used for.
But they work out very perfectly. And what you really did nicely with there is you used the Helmholtz coils, but I bet you could do a whole bunch of stuff with Helmholtz coils, yeah?
Oh, yes.
What are the great things you can do with that?
That's the whole reason for it is to have a uniform field so that then you can put things in here, see how much torque you have on a magnet and things like that. And of course, you can just use a single coil if you want to do other experiments as well.
And these are available if people wanted those experiments? Could they find them?
Yeah, they're in our library.
In our library, right. Thank you, Ann. So, ladies and gentlemen, Ann Hanks and the Helmholtz coils, very nicely done. And so, ladies and gentlemen, you have now enjoyed 17 straight physics demonstrations, 3.5 hours of physics experiments to bring into your classroom. And so now it's a great opportunity for us to thank the folks that made this all possible to you. A big round of applause to Nolan on the cameras. Thank you, Nolan. Janet on the keyboard and answering all your questions. And of course, our great physics crew here, Mr. Dan Burns, Mr. Jonathan Hanna, Mr. John Hanks, Ann Hanks, J.J. Plank, Brett Sackett. Did I forget anybody? You got John. I think we got them all here for you today. And of course, I'm JP, where the P today stood for physics, and we're really glad you enjoyed us. Ladies and gentlemen, from PASCO Laboratories, we wish you the best physics day ever, and thank you for joining us. Have a good day.